Institute. We've got Sustainable Sun Systems, Middle Georgia State University, Firestarter Fab Lab, and we've got some folks from Joint Base Andrews to talk to us.
All right, along with other AIF Spark cells, we look to bring you a lot of future events like this, workshops that the rest of the Air Force and other Spark cells can benefit.
So if you could join us on social media, make sure you hit subscribe, and that way you'll know anytime we have an event like this.
Oh wait, we have a very special guest. Who else do we have too?
I'm glad you asked. We've got Mr. Robert Manning, Dr. Robert Manning, who's going to show up today. He's landed on Mars more times than you have.
I have no re-attacks on that one. However, please continue to join us with the Spark Cell, and we'll hopefully deliver you guys more innovative projects and successes. So let's get started. So without further ado, we're going to roll right into our special guest because we know Mr. Robert Manning is waiting for us. So I'm just going to give a little introduction to Robert Manning. Rob Manning is Chief Engineer for NASA's Jet Propulsion Laboratory, as well as Chief Engineer for JPL's Engineering and Space Directorate. He has been designing and testing and operating robotic spacecraft for nearly 40 years, just as old as I am. Reaching Jupiter, Saturn, Venus, and Mars, the great rovers of Spirit, Opportunity, Insight, and Curiosity all fall under his belt. He has received 4 NASA medals, 2 honorary PhDs, and has a minor planet actually named after him. Space News magazine named Rob one of 100 people who made a difference in civil, commercial, and military space. However, getting to Mars is very difficult, and let's look back into history and see how difficult it really is, and also rewarding.
Although we've done it before, landing on Mars is hard, and this mission is no different. The process to get from the top of the atmosphere of Mars to the surface we call entry, descent, and landing, or EDL. It takes thousands of steps to go from the top of the atmosphere to the surface, and each one of them has to work perfectly to be a successful mission. The process starts well above the top of the atmosphere of Mars. The cruise stage faces the sun. It also has its radio antenna, which faces Earth. But now we don't need the cruise stage. Its job is done. The next step, just 7 minutes before arriving to the top of the Mars atmosphere, is to separate the cruise stage. Before you hit the top of the atmosphere, though, the space capsule has to orient itself so that the heat shield is precisely facing the atmosphere. Now the fun begins. The vehicle is moving at nearly 13,000 miles an hour, but it's hitting the top of the atmosphere at a very shallow angle, 12 degrees. Any steeper, the vehicle will hit the thicker part of the atmosphere and will melt and burn up. Any shallower, the vehicle will bounce off the atmosphere of Mars. At the very top of the atmosphere, it's about 70 miles above the surface of Mars, and the air is starting to get thicker and thicker and thicker. As it does that, the temperature of that heat shield gets well over 1,000 degrees centigrade, enough to melt steel. Over the next 2 minutes, the vehicle decelerates at a backbreaking 12 Earth Gs, from 13,000 miles an hour to about 1,000 miles an hour. At about 10 miles above the surface of Mars, a supersonic parachute is launched out of the back of the vehicle. 15 seconds after the parachute inflates, it's time to get rid of the heat shield. 6 pyrotechnic devices fire simultaneously, allowing the heat shield to fall and tumble away from the vehicle, exposing the lander to the surface of Mars. 10 seconds after the heat shield is dropped, 3 pyrotechnically deployed legs are released and locked for landing. About a minute later, the landing radar is turned on, sending pulses toward the surface of Mars as the vehicle starts to try to measure how high it is above the surface and how fast it's going. At about a mile above the surface of Mars, the lander falls away from the back shell and lights its engines. And very quickly, the vehicle must rotate out of the way so that the parachute and the back shell doesn't come down to hit it. The last thing that has to happen is that on the moment of contact, the engines have to shut down immediately. If they don't, the vehicle will tip over. So if all the steps of entry, descent, and landing happen perfectly and we are safely on the surface of Mars, we'll be ready to do some exciting new science.
Touchdown confirmed.
Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
through just to about 45 minutes, see if I can do that. I'm notoriously bad. Internal is your mission. Use accepted is to go, time out. You're right out of time. Okay. Because I'm not good at time management. I have other people help me with that. So let me share some slides I have. They don't look pictures, and pictures are worth 1,000 words. And so let me see if I can't figure out how to share my screen here. I've got this share screen button. Okay, one quick second. Do that, and then is it working? Let's see if I can get it to full screen mode.
Please good, Rob. It's good.
How does that look?
Looks good, Rob.
Excellent. Okay. Yeah. So okay. I'm not going to be talking about 3D printing or FM or any other technology. I'm just going to talk about this is probably just for fun and to inspire you and to try to and to remind us all that it takes a village of people to make innovation happen, but it also takes a lot of creativity and imagination. So one of our challenges for going to Mars is that we've actually haven't been there very much, and so it's the process of getting there and exploring the surface has been a wild ride because we learned so much. And if you're trying to go to a place you've never been to before, it's hard to know whether you're prepared or not. I'm sure some of you've been there before. It's hard to get people. It takes a lot of imagination to visualize what you're going to be getting yourself into when you get there. So let me talk a little bit about that. So first of all, so you saw a little bit. I was on Mars Pathfinder. This is the secret behind autonomous rovers. We take little people, shrink them down, stuff them inside rovers, and there's an example of one of our early prototypes. Actually, it's my daughter sitting there on Sojourner, a model Sojourner rover in our sandbox where we did our testing of our lander. A former conference room that I converted by going to Home Depot and buying lots and lots of play sand. Seriously. So that lander now is at the Smithsonian, but we were using it for testing at the time. Later on, and I'll tell you the story of how we got here. This is me with Opportunity rover. We built that in amazing stories there of how we got those two rovers to Mars, Spirit and Opportunity rovers, back launching them in 2003 and landing in January of 2004. And later on, we went on to do bigger things with this behemoth rover called Curiosity rover, which went to Mars 2012. Still there. Watch all of our rovers. Yeah. All of our rovers, by the way. Remember, it's a one-way trip. You send your stuff there, never comes home. That will change someday. But this monster was sent to Mars and it's still working fine. All the other rovers have since passed their life, and with this rover still going strong. And there's another picture of that rover. You playing around, and this is our sandbox. This is not play sand. This is garnet that turns out play sand's not a good idea because you stamp on it long enough, just like real playgrounds, it just turns into fine dust and gets stuck in your lungs, and it goes nasty. So we decided to use garnet in the future. Then later on, I went in to build Chief Engineer for something called LDSD to test supersonic parachutes and supersonic inflatable devices. We launched over out of PMRF, out at Kauai. It's the Navy facility there where we launched this on a super large high altitude balloon and launched it at about 180,000 feet, something like that, and it went up 130,000 feet, and then launched it to 190,000 feet with a big Star 48 rocket pushing, so we could test supersonic parachutes in the density of Mars condition, way up high above our Earth. And so let's just talk about Mars a little bit. It's the Mars story. I was just graduating from high school when these two missions, Vikings 1 and 2, landed on Mars. So you saw that sequence of events that I described with my pen on a glass wall. We used that very same sequence. What was different about, and so this is almost identical. would use these throttled engines. There were, see my cursor. See that gold thing right there? Well, we can see this in the Air and Space Museum in Washington D.C. And you can see this is one of 3 thrusters clusters, and there's actually a bunch of little thruster nozzles there. The reason that there's more than one nozzle is because we realized on Mars, and this is sort of true on the moon too, but mostly it's more concern on Mars. These thrusters actually dig holes in the dirt, and so we had to spread out the thrust plume on Viking days in order to avoid having big holes that would be created that could affect the landing itself. So the landings are real art. Just the art of turning your engine off at the time of touchdown turns out to be really hard. You might say, well, what's wrong? I just touched the ground, turn the engines off. Well, by the time you've made that thought, you've already bounced or started to flip over. so you have to be pretty quick at it. So the purpose of these missions was really to find out whether anything was alive on Mars. And so this thing had an arm. You see the arm right there in front of you, the big black thing? It's reaching out. It had 3 biomedical science laboratories that actually looked, biological laboratories that looked to see if there was something alive there. In fact, what it did was it actually put the dust in there, put a little bit of food, warmed it up, and then sniffed it, looking for the exhaust, as it were, of microbes that would come alive in the sugar water. In effect, it wasn't exactly sugar water, but it was nutrient laden. So the idea was is to look for life, and the answer was Mars looks it's not very lively. In fact, there were no little green men anywhere. There was no green plants. It looked a lot like somebody had taken the moon, made it bigger, and spray painted it red. And it was. In fact, it turns out it was spray painted. But it wasn't the moon. It turns out it's much more interesting than the moon, and it has a much richer story. But at the time that Viking runners, they were a little disappointed, to be honest with you. They thought, shoot, there's going to be something interesting here. I mean, certainly they already convinced themselves there are no canals on Mars, no aliens. But these scientists, the people who believe that Mars was inhabited somehow. But anyway, so that was Mars. So what happened was by the way, Vikings were not the first to use the land successfully. We actually give credit to the USSR, who had many attempts on Mars. They had one attempt that they think worked for at least a few seconds, and it didn't crash. It seemed to land it, and it survived for a little bit. And I'm not showing you all the Mars failures, which I think these are the ones that seem to work even for a few minutes. The Mars 3 will work for a few minutes. Vikings 1 and 2 lasted years on the surface, and about 4 years. And about then, after that, the United States lost interest in Mars. So for 20 years goes by. Nobody's going to Mars. Nobody's landing on Mars. And then NASA says, we need to show that we can go back to Mars. The trouble with these big Viking missions, they were really expensive. In today's dollars, it was something close to $4 billion. And in the space biz, there's planetary robotics world, that's pretty expensive. They said, can we do something cheaper? Can you guys find an innovative way to land on Mars and get there that isn't going to cost a fortune and can be done much cheaper? And so the era of the faster, better, cheaper was born in the early 90s. And so my teammates and I were chartered with building a vehicle that was a lot cheaper than the Vikings and a lot simpler. So and of course you can see there are other missions that happened since then. There's these 2 Spirit and Opportunity rovers that bounced on Mars, just like that one. The Phoenix rovers, Phoenix lander that looked a lot like the Viking landers, except they didn't use all the energy elsewhere. Curiosity rover, which you see, and the inside, which is where you just saw what I made for. So I think you can send that into that vehicle, which is identical to Phoenix. And then 2020, which I'll talk a little bit about, which is just been launched. It's on its way to launch right now. Ran the cables through, so I could operate the lander and talk to it from there. And so we would do our testing and rover deployment testing and do our mission testing in this little room. Of course, we had to test these airbags. So, you know, these airbags, there's 17. Oh, I don't know. I've got an automatic forward. Sorry about that. So 17 feet diameter. That's a pretty big. And they were about almost 100 kilograms. So, 200, 220, over 200 pounds of fabric. Vectran fabric. This thing had to hit the ground up to 70 miles an hour, not just with a vertical impact, but a lateral. And by the way, this thing bounced like a banshee. You would this had you remember those super balls we used to play with as kids, those really super hard ones that you dropped, and pavement was so much fun because they had such a great coefficient of restitution, which means that fraction they came back up, and they would just bounce like a mad. We tried this in a vacuum chamber because Mars is almost a vacuum, only 1% the density of Earth on Mars. Mars is further from the sun. It's colder. It's got less gravity because it's smaller, and it's got hardly any air, just like 1%, and it's all carbon dioxide. And so the cool thing is we inflate this airbag to only 1 psi, and then this thing bounces. This thing bounced like I said, banshee. It would go when you dropped it from the height of this was the world's largest vacuum chamber. This is in Sandusky, Ohio. at the SPF facility at Plum Brook Station, run by NASA. It's a massive vacuum chamber. It's 110 feet tall and 80 feet wide. And we dropped it from the ceiling, and boing, it would just bounce like crazy. We finally got it built, tested. This is us doing our final touch-ups of the vehicle. Then we stuffed it inside the aeroshell. That's just in front of it there with Marvin the Martian there on top. And then we finally got it off the ground, launched it, and then oops, sorry, it's on my phone. And then 7 months later, we landed, and you saw the little video of me. I was the chief engineer for Pathfinder, and I led the team, and so we got it to work, and so we were able to explore Mars. This little area here, you can see all the rocks there as far as the eye can see. We learned how to drive a little rover. Oops, sorry there. This little Sojourner rover. One of the challenges about driving a rover, this is another little faster, better, cheaper thing. This is only $25 million for the whole development. Now it sounds like a lot for a rover, but it's pretty hard to build a rover that works. And it had some really cool new technologies that were also very cheap. We use things like a laser light stripers that produce these little laser stripes, and there's a little camera there with an infrared filter, with the filter on it that only looked at saw red, and where those stripes were, it showed up on the CCD image that would take. If you're sitting on a complete plane, those stripes would show up in a particular pattern that you knew you were on a flat plane. So the rover didn't have to do any math, didn't have to do any three-dimensional rendering of the scene around it. So we could get away with a single 8-bit microprocessor, an ADC85, a very, very simple little processor that allowed us to do all this, to do the math and to do the driving. But yet, nevertheless, we would still the vehicle would get lost, and sometimes it would inadvertently climb a rock, and including this awkward moment when Sojourner inadvertently backed up that rock on its left rear wheel. And to face the camera, the rear end of the vehicle, actually the front of the vehicle, facing us there with this it's single science instrument there, a very simple alpha particle X-ray spectrometer that looked for elemental composition of rock. So what did we learn? Well, in this mission, we didn't learn a whole lot of science. It turns out what we learned, though, is it's possible to go to Mars and learn it's possible to drive on Mars. The one that we did learn is that when you're only this high above the ground, when you're only about less than a foot above the ground, rocks that are 1.5 feet tall are very big, and you are very little. And so we realized we need something bigger, a little bit more, not quite car size, but more like a golf cart size to actually do that exploration. Oh, by the way, I know you may have seen this. Our lander also showed up on the Martian movie. This is a scene from The Martian. Actually, I helped make that model for them for the movie. It was fun. They used our lander. Actually, Andy Weir, the writer of the book, used our lander. He was a fan of Pathfinder and of our team. He used our lander as a way for the astronaut, Mark Watney, to communicate back to Earth. You guys remember that? I like that movie. I'm a little partial, like I say. Anyway, we had, so years ago, so the next mission we had was Mars Climate Orbiter. So Mars Climate Orbiter, and there's two vehicles, an orbiter and a lander. So this is another low cost. We pushed the team to the limits. They decided they were going to build this is where our friends at Lockheed, we asked them to build a orbiter and a lander for the same price of all of Mars Pathfinder, which was already super cheap. And they said, oh, well, we can give it a try. So they did, and they did a great job. But we worked with them very closely. And so, between the two of us, working us navigating it and them designing it, we made a big mistake. So, we talk about finding places where you could fail safely. Well, that's what testing is all about. You find test venues where you can actually try things out, try out these ideas. Let me make sure that I'm not, see how I'm doing time-wise. And so we try things out. And so this case, Mars Climate Orbiter inadvertently became a lander. You can imagine that. So you may have heard about this. Remember reading about the English to metric conversion error that lost where his mission was lost? Well, this was the one. This is the one. What happened was, see that solar panel? See, all of you guys you might think that you might not know it, but you're all rocket scientists. So imagine, look at that solar panel, and it's facing the sun. You're on your way. Imagine that thing's on its way to Mars, and it's and for months and months, it takes about 7 months to get to Mars, and you're on the way there, and the sun is pushing on your solar panel. And so you imagine you're seeing your solar panels right here. So imagine that light bulb here facing me is illuminating my face and my solar panels. And well, solar pressure, just from the impact of the photons themselves, pushes me like a weather vane. I have to turn it around again and free face the sun all the time because the pressure is causing me to act like a weather vane. Well, in the process, the vehicle had to fire its thrusters to orient itself. In the process of firing its thrusters, it moved itself to the left. Yet we were measuring from Earth where it was by measuring its radio signal delay back to Earth. By timing it very precisely, we can figure out how far away it was. But we couldn't see it move across this field of view, the sky. We're looking up here with our radios on Earth, so we can't see them. We can't see these things. They're too small. They're too far away. We have to infer where they are from the radio signal. Well, so it turns out it's firing thrusters in such a way that it was putting a lot more thrust to the left. And we were doing the math, figure out how much to the left it was moving. And we were told, everyone thought it was being told in the units of SI metric units. And it turns out it was in English units. It was in pounds force and not in newtons. And there's a factor of 4.45. So we were off by a factor of 4.5 and are underestimating how much those thrusters are pushing it. And it was moving to the left. And guess what was to the left? Mars. So this thing came along, and when it got to Mars, it got real close to the surface. It got closer and closer. And as it flew past Mars to fire its engines to get itself in orbit, it hit the top of the atmosphere. How about that? So that's not a good way to fail. It was, failing at national TV is not the way to go. I just don't recommend it. It just has nothing but tears, is what I can say. This is where Jay Leno, some of you might remember Jay Leno, the stand-up comedian. He stood up and says, "Well, it just goes to show you don't have to be a rocket scientist to be a rocket scientist." And we're going like, "Oh, yikes!" Anyway, so we had 2 missions. I said 2 missions. Well, this is the second mission. Which was on its tail, headed to Mars at the same time. It was only 2 months behind it. And it was this one. It was it was a lander, and this lander it was also a faster, better, cheaper mission. And one cost savings measure is that they didn't have a radio that would work while it was landing on Mars. So they figured they don't need to talk to it when you're landing because it's all automatic. Mars is 20 minutes away by light time, right? And so there's no way we can joystick this whole thing from Earth. We just have to program it to do all those things. And we just sit on Earth. When you see us jumping up and down with our blue shirts and things like that, screaming, well, it's not because we're controlling it. We're just kind of sitting here watching the data stream back, such as it is. In this case, there was no data stream back at all. We're just sort of sitting there having a cup of coffee, waiting for the vehicle to land safely and phone home after it landed. Well, the time came for phoning home. 5, 4, 3, 2, 1. Nothing. I'm sitting there. There's a control room. There's a glass. I'm standing behind the glass. I'm looking at the countdown timer. I'm looking for the point where the signal pops up. No signal. We never heard from it again. This lander is missing in action. It's somewhere near the south pole of Mars. And if any of you happen to go to Mars someday, some of you may, could you please keep your eyes peeled for this thing? I have a feeling it's bits and pieces. We've got terabytes of data we've taken from orbit since landing many years later from the Mars Reconnaissance Orbiter, which is basically a spy satellite around in orbit on Mars, and covering that whole area, and we can't seem to find it anywhere. There are little cracks and crevices like the one shown here in the middle where it might be lurking in. I don't think so. I would have seen a parachute, back shell, heat shield, other stuff, even a cruise stage crashing. Debris would still be there somewhere, but I can't find it. I'm pretty sure I know what happened to it. I think it broke up during entry, and I think we know why. But anyway, so this is kind of depressing. So again, failure on national television. This is not a good thing, not a good idea. And I'm thankful, by the way, that there are no people on board. I mean, I could not live with myself if I had human astronauts at lives at my fingertips here. It's bad enough to crash a robot. Anyway, so innovation. So we had to come up with some recovery. So I didn't mention the fact you can only go to Mars every 2 years. You have to wait for Mars to go around the bend, around the sun once before you can go. And that launch window is only 2-3 weeks long. And so what we did was, so we had to figure out what to do next, because we couldn't land. We didn't know why that lander failed. So we had another identical lander that was being built. We didn't know what to do to fix it, because we didn't know why it didn't land or why it crashed. So one of my buddies came along and said, Rob, hey, why don't we just take Mars Pathfinder over there on the left? There's that same picture again with the tetrahedral shaped lander with the pedals closed, surrounded by airbags that bounce the surface. And we get rid of that little rover, Sojourner rover, and we convert that white box with the JPL letters and the US flag on it, and we put wheels on it and solar panels on that. And so there we go. So we did. We make a tetrahedral shaped rover that would fit inside a tetrahedron, and we'll unfold it and stand it up, and it will drive off drive off its lander structure. And so that's what we proposed. And we proposed that to NASA in May of 2000, about 5-6 months after the failure. And NASA, to our shock, bought our idea, and so we built 2 of these, Spirit and Opportunity rover. We use the same landing technique, entry space capsule, supersonic parachute, heat shield. Entry capsule, heat shield, supersonic parachute. Heat shield comes away. Lander repels down a 20-meter long rope, and airbags inflate at the last minute, and solid rocket motors in the back part of the space capsule fire at the last instant, slowing you down from 200 miles an hour to 0 miles an hour, about 10 to 20 meters above the surface of Mars. That'll work. That's what we did. And so it worked out well. And we because we came up with the idea first, we had to hire a principal investigator. It was his instruments. This is the illustrious Dr. Stephen Squires. He's a very funny guy, and he's a wonderful principal investigator and a wonderful researcher. So he put the scientific story behind this idea that Mark and I worked on, and made it into something that was really a scientifically amazing mission, because now he's a geologist, and he can make roving geologists out of our rovers. But this is one of the things that's this is the end of the robotic arm, and you can sort of see there's a Mossbauer spectrometer, another alpha particle X-ray spectrometer. There's a little thing to grind away the weathering rind on the end of the rock. I've got to show you this. He sent us to this at a very stressful moment when we weren't sure we were going to launch. So he made this little video. He made this little video for us. Let's see if this comes through. It may not come through. And there's the rat. We call it the rat. It's speeding up. Now it's going to the rock. Now it's going to grind a little piece of the rat. Uh-oh, what's going on? Oh, no. Well, that was just funny then. We needed that humor. I tell you, we were so stressed out at that time. So testing was important, and we were testing our airbags. We built a new sandbox there. We would try out the air inflator on our friend John Wirtz, and we try to have a little bit of fun while we're doing it. So I'm not sure why this display is doing this. We would try out driving, egressing off of our lander with different orientations. Finally, our rover gets really complicated. This is what the rover really looks like in the front end. All the models and everything don't do it justice, because it's actually very complex. A lot of wires. We have cameras. We have the robotic arm, and just a lot of wires too. It's a lot of wires. We finally got these 2 things off the deck in December. In June in 2003. They were 3 weeks apart, and they follow each other to Mars. We finally got them to Mars, and I was very relieved. You saw, and got that to. I led the systems team and the Intercent Landing development team, and we got to take a picture from space. This is our lander. We happened to land inside a little crater, bounce into it, called Eagle Crater. It's kind of like people used to say, we were joking, like, this is a hole in one. Yeah, it was. We were pretty lucky. This is the other rover. This is Spirit, having driven off its lander, and we got a chance to check out the heat shield, because the heat shield had crashed only about a quarter mile away from us, and I was able to take a look carefully at how well the heat shield material thermal protection system lasted. We did incredible exploration. We saw these strange looking rocks inside. Now these rocks were formed in water, and so everywhere we looked, we found rocks on both sides of Mars, because these landed in two different places on Mars. Water had clearly altered Mars, and we confirmed that Mars was in fact a wet and Earth-like world about 3.5 billion years ago, a long time ago. But it was you might have actually, when you went to Mars back then, you would have found oceans. Now, was that water habitable? We didn't know, but we knew it was wet. We learned that for a fact by exploring these surfaces of these craters. These rovers got a chance to get some pretty decent tilt into them. I was surprised that we would be so brave to do this, but we had 30 some degree slopes that we were driving along, struggling along to explore the edge of Burns Cliff there. A lot of strange surfaces of Mars, with the wind on Mars, which despite only 1% the density, that little bit of wind, a little bit of thickness of air is enough to cause sand to hop along the surface. It's called siltation, and it grinds away rock into these wonderful airbag eating shapes. Didn't know about that when I was testing airbags, tell you that. And so we explored Mars, left our tracks there. We explored larger craters, and this is an astronaut stuck in there for scale. This is Victoria Crater. We went up to climbed on tops of some decent hills, Husband Hill, and we left lots and lots of tracks on Mars. And those tracks will probably be there for, a few thousand years, I suspect, and more craters. Did our first stratigraphic section of Mars, to looking at the layers of time, because these craters that were formed not that long ago in Mars history, probably 100 million years ago or less, we produced these wonderful road cuts, and you can just go through and see all the layers and basically go back in time by just driving down those layers and analyzing the mineral composition as you went. So of course, these are done by people. We've got great teams of people. People from all over the world are helping us with this stuff. Of course, it's still costing us millions of dollars. This project was about $870 million, not $150 million or $200 million for Pathfinder. But it was worth it. And they lasted a lot longer than we expected. We designed for 3 months, but they actually lasted for years. So let me quickly segue, because I'm almost out of time. So you can see we've got a little trend here. We want to build big. If we start here, we wanted to build a bigger rover. Why we want a bigger rover? Bigger is not better, but we needed to be able to send laboratories to analyze. The next question was to find out what the habitability of Mars back when it was wet. Was that water a good place? Was the soil such that, and this condition such that the living things could survive, the living things that we understand on this planet? And so we needed a laboratory, so we needed a bigger rover, but we didn't know how to bring it to Mars. And so we didn't have any good suggestions on how to do it. We had to come up with ideas. And so about the same time we were inventing Pathfinder, actually, we were trying to invent how to do this after the failure. So again, failure is sometimes the mother of invention. And it's certainly a necessity as well. But our teammates, we came up with all these different ways of permutations for landing, and with giant airbags, outrigger landers that won't tip over as easily. We could lower it on a rope and fly away. Yeah, that's just stupid. And then land on a pallet and try that. We even tried ideas where the rover was stuffed in a garage underneath the lander itself. ironically, about 3 years later, after experimentation on Spirit and Opportunity, we realized that we can control it, like helicopter pilots, Skycrane pilots could do the very same thing. And so we could Sikorsky helicopter pilots, they have enormous control. And if you wire it up properly with the right bridle configuration, you put it through the center of mass of the vehicle, you can control it with various precision. So people ask, well, wasn't the Skycrane architecture the most risky thing? I said, well, no, it was just the least unsatisfactory to land. So landing us on ropes is what we ended up doing. We started building it. We put the vehicle together. This is what the inside looks like. You can see how complex it is. Many miles of cables and lots of electronics inside and laboratories. It's a very complex machine. This is what the front of the rover really looks like. It's also extraordinarily complex. Finally, we launched this up in 2012. We landed it, and I turned blue again. You might ask yourselves, when we land these things, are we happy? No, we're not happy. We're relieved, because all the things for years we've been thinking about all the ways that we've screwed up and what we might have forgotten. And so this is a chance. I was chief engineer for this mission, and I can tell you, I was very relieved that all my worst fears of what could go wrong that day were gone in an instant when it landed. So this is where we landed. So let me check my time here. Yeah, I'm really running out of time. I'm out of time.
We switch over to questions now, if that's okay with you. So
yeah. So yeah, let's do that. So this is just the mountain where we landed, and now the rover Curiosity now is right up here in the middle. Okay, so I'm going to go stop sharing. This is a good time to place to stop, and I can just wing it with that. Okay, excellent. So that's some of the story, and just a reminder that there's another rover on its way that looks a lot like Curiosity, but this rover's got a new mission, and it's got a new what's more, it's carrying a helicopter that's going to fly around the surface of Mars for a little bit. And its mission, this new rover's mission, is to collect samples for sample return, and that's what this vehicle is going to do. It's not going to bring them back. It's another mission, but it's going to put them in special tubes and leave them on the surface of Mars we picked up a few years from now. Okay, I'm done.
All right, Rob, thanks so much, and great stories. I mean, Rob did mention a lot of failures there, and a lot of this stuff isn't really seen, so it's very difficult to get, all those different rovers over to Mars. So I'm going to turn it over to questions now. So we have some folks ready to fire away with some questions. So first, I'm going to go with Airman Loxon. He's going to present a question to you. Go ahead. Go ahead.
How are you doing, Dr. Manning? So you're talking about failure. In terms of the airbags, was there a bunch of different designs being incorporated to the airbags, or was that the first and final design that you guys came up with?
Oh no, quite a great question, Airman. You're fantastic. So we actually our first attempts at testing those airbags. We did one of the things is we were trying to simulate the impact of those airbags on a grazing surface. So because those rockets, when they're swinging like this, when they fired, slow you down, but also they can impart horizontal velocity, we needed to be able to test an impact on rocks of this 16 foot tall airbag, this beach ball with a 300 some kilogram lander inside, and hitting this rock surface at 70 miles an hour. So we tried doing simulations with special impact codes, software that allows us to model those kinds of impact. None of that was actually working. We didn't believe it because it just wasn't converging. So we had to take it to the world's largest vacuum chamber, as I saw. But we built a giant 60-foot tall ramp, and we bolted sharp rocks to the ramp, and then we took the airbag and we pulled it down with this massive bungee cord system, so it actually would hit the rocks at about 70 up to 70 miles an hour. And as you can imagine, didn't work first time. The airbags tore themselves to shreds. So we redesigned the airbags, tore those to shreds, redesigned the airbags, tore those to shreds. We did this 4 times, and finally we got a design that would work. In fact, we had to, even the outside design was changed. You can see there's multiple lobes on those airbags. We started off only 3 lobes for each of the 4 sides. We went to 1, 2, 3, 4, 5, 6 lobes per side, and that was that made a big difference and reinforced it. Turns out those airbags are such that you can actually climb inside. If you can unzip them and climb in, you can go from one part of the airbag to another part of the airbag to another part to another part. They're all one giant volume. It's about 50 cubic meters of gas space in there that allows this thing to be compressible when it squeezes down. That's something that airbags do really well on Mars that they don't do in Earth. You can, if you fill up a basketball on Mars, that's the same pressure or basketball gauge pressure on that you do here on Earth. Unlike on Mars, unlike on Earth, you can take this basketball to either the moon or Mars, or take it outer space. Try squeezing it. If you guys become astronauts, try to take a basketball with you, fill it up normally. Don't fill it on Earth, fill it up there, and you'll realize you can squeeze it and put it in your pocket. It's kind of amazing. It's very compressible because of the difference in pressure as being so different. And so we did practice. And so trial and error was an important factor. Even then, we weren't sure we had done it right because there's so many different possible orientations and rock shapes. I did not know about those sharp rocks when we were designing the airbags and testing them. Didn't know about them.
Thanks,
Had I
Ed.
known about that, it would be big trouble. So next question. I'm sorry. Go ahead.
No problem. And we have a special question. So we have a wide audience here, and we have Georgia Tech, and one of the professors actually brought his daughter. So his 13-year-old daughter, Ray Lynn's here, and would like to ask you a question. So.
All right, Ray Lynn, come on up. Georgia Tech, woohoo!
Talk a little louder.
Okay. So what exactly are you looking for on Mars? Like, I get you're looking for, like, if it's habitable, but like, what exactly are you trying to achieve by going there?
Great question. Now, it depends on who you are. Thank you. What a great question. So it depends on who you are. If you're looking to find out whether Mars is a habitable place for us to live in, you'll be looking for where the water is, how to extract the resources so that humans can use the water to drink and as a source of oxygen. Because remember, H2O, there's O in water, you can drink it. But we're looking from a scientific perspective. We would like to know, this is the question. Okay, all of us, the scientific community strongly believes, and as do I, that life got started 4.5 billion years ago. And both on Earth and Mars, at the same time, the solar system was formed together. And the question is how did it get started, and what's the story at Mars? Did Mars have a similar kind of, if the conditions for the formation of life were the same on Earth and Mars, why wouldn't Mars also have had life get started? Is it possible that life actually did get started? In fact, Mars might have been more habitable than Earth was about the same time. And as we've learned from giant meteorite impacts that have sent rocks to outer space from Earth, and we found meteors that landed from Mars on our own planet. We found rocks from Mars that landed in Antarctica. Though it's possible that life could have transported itself inside those rocks, single cell organisms, flown across and landed and seeded each other. So imagine this. What if life got started on Mars? Then a meteor came along, launched some of that life over to Earth, lands here, and it turns out that we are all descendants of those Martians, which means that you are a Martian. Now, I thought so. You look like a Martian to me. No, so that's one way. So trying to understand the origins of life, find out where life got started. We firmly believe that the web of life is ubiquitous. We see life in every corner, every possible pocket where there might be even a little bit of water. On this planet, deep down below your feet, miles below in the rock, we found it in oceans everywhere. Life wants to live, and we want to know why life isn't where life could be, and in our solar system. And many of us believe that if we look hard enough, we might find signs of it.
Thanks, Rob. I think we're pretty much out of time. And she did look like a Martian because she was wearing red. So
yeah, that's what I thought.
Thanks for taking the time today and truly blessing us with your presence. I said it before, I'm going to say it in front of everybody in YouTube virtual world and here, you are one of the heroes of our mankind and our generation. And, you know, and really, it's truly remarkable and inspiration for airmen and folks to listen to you across the world and you know, share your stories on Mars. And I'll probably get to where Steve said before that you've landed on Mars more times than me, but maybe we have plenty of airmen here in Space Force that one day may be on Mars. So thanks for joining us, and thank you so much for blessing us with your presence.
Thank you very much, Colonel Biz. Thank you. Thanks very much for inviting me.
Rob, one more thing. You know, and we have a 3D print workshop here, and it's you know, it's very hard to give you this coin in present, but we have a 3D printed coin from our Spark Innovation Hub. I'll send it over to Dolores to give it to you, and make sure you have it over there and pass it to you. Thank you so much.
Thank you very much. Thank you all. I really appreciate it.
All right, and we'll move over to intermission now. Thank you. we were able to collaborate with the community and develop a task force so that we can get 3D printed solutions out to the community and folks here on base. And one of the driving forces behind this was Middle Georgia State University and the Firestarter Fab Lab here in Warner Robins area. So without further ado, I'm going to turn it over to Jay Flesher from Firestarter Fab Labs.
Let's start with the video, guys.
Maybe you have a great idea, but
Or are those New Year's resolutions coming along?
or maybe you have a great idea, but you just don't know how to get it off the ground. Maybe you wanted to learn a new craft. Well, over in Houston County, you can accomplish those things at the Firestarter Fab Lab.
I'm taking you inside to show you how some people are getting a lot more from those classes than just a new set of skills.
Any kind of knowledge they have, any kind of ideas they have, they can take it and run with it.
At the Firestarter Fab Lab in Houston County, people can see their ideas come to life. People like Ramey Chanel, a hobbyist turned entrepreneur, thanks to his know-how and the Fab Lab's resources.
We started making cutting boards, and I was laid off from my job the day that my business went live, and when it went live, it took off. I've even shipped to the Dominican Republic.
Now he's helping others to do the same, any skill level, any age.
From 14 all the way up to 80.
One of those is Karen Lloyd.
I love creating things.
But because of health challenges, that hasn't always been easy.
I've been diagnosed with lupus for over 15 years. You can't work 40 hours a week. You have a brain in your head that you could use. What do you do with that? And then I find the Firestarter Lab.
At the end of the day, our goal is really to take our community and move from a consumer community into a producer community.
Organizer of the lab, Jay Flesher, says they wanted to give people hands-on training and hopefully inspire more businesses here in Houston County.
By giving them access to tools and giving them the knowledge of how to do that.
From welding to woodworking to printing, just about anything you can design here on the computer can come to life right here.
Probably one of the greatest things I've ever done. It was awesome.
Lloyd came to the lab wanting to learn something new, but since then, she's left with a lot more than her creations.
Really give me self-confidence and a sense of purpose in life, that when you're sick and you do face challenges, that sometimes you don't feel like you have.
So whether it's creating a future business, tackling a hobby, or a newfound sense of pride, anyone can learn to blaze some new trails.
This is very empowering.
The lab.
The Community and Economic Development Manager for Flint Energies. So yes, I do have another job outside of Firestarter Fab Lab. And really the Fab Lab was created through a grant through the Flint Energies facility. Now we're talking about 3D printing today, but in just really it takes a bigger community process to get to a point where you have access to equipment and people and create that community. And that's sort of what the Fab Lab's about. You know, back in 2012, we really started up. The reason why we're starting up, we were trying to answer some questions around BRAC, Base Realignment Commission study, and it had to do with a couple of topics. And it had to do with recruiting and retention STEM professionals. It had to do something with diversifying your economy, and it had to do with organically growing STEM proficient students. So that was really what we were sort of trying to really do when we set up the Fab Lab. Now, the Fab Lab, again, was set up through a grant with the Flint Energies in conjunction with the school board here in Houston County. It's a built 7,000 square foot building over on Quarter Road. It's got digital manufacturing in the front, it's got woodworking in the middle, and metal manufacturing the back end of it. We don't certify you in anything. It's all about instigational. We want you to come in and ask questions, say, hey, I would like to do that. I would like to program a game. Well, what we do, we start gathering people together that have the same interest, and we cluster you into doing how to do that. Well, the same thing goes with 3D printing. When we started to look at 3D printing, we had clusters of people that interested. Not everybody is interested in 3D printing, but when you start to gain these clusters, all of a sudden the innovation starts to pour out, and that's sort of where the Fab Lab got us going in.
Good morning. Gary Hart. I'm with Middle Georgia State University. I'm actually the military affairs guy over at Middle Georgia State, but I also work in the Center for Software Innovation. So the Center for Software Innovation, the CFSI, actually started up back in November of 2019. So you talk about good timing, right? In an unfortunate time where a lot of innovation centers were popping up because, especially here, there was a call in Middle Georgia for innovation, right? So answering that call between Firestarter Fab Lab, Mercer University, places like the Spark Hub here at Robins Air Force Base. But we figured out that, you know, as we moved on, and, you know, a lot of these innovation centers were in their infancy. Well, I'll tell you, in early this year, when the pandemic struck, there was an international call to arms for PPE. So when you look around, we started to kind of find our legs and figure out, all right, so as innovation centers, the collaboration effort that needs to happen for PPE generation, who's going to do that? Who's going to step forward? Well, I will tell you, Jay Biscard and his team here at the Spark Hub at Robins stepped forward and said, you know what? We know a lot of people. We have a lot of collaboration efforts going on. Love to be able to put something together with our community partners and actually start answering that call. So Mercer University, so their engineering, the ability for them to be able to help engineer solutions, even if, and again, you know, there are a lot of entities out there that are operating in constrained environments, especially budget-wise. So the ability for Mercer to be able to help engineer solutions, but not exactly have the capacity or flexibility for mass production, again, there's still a piece, right? So then you go forward and you have folks like the Firestarter Fab Lab who have the capabilities, who have the production assets to be able to turn out things like this, along with the brand new Center for Software Innovation over at Middle Georgia State. All of a sudden we have a crowdfunding or a crowdsourcing effort that we can actually mass produce and get pieces of PPE out to our first responders, the medical communities, you know, some of the veteran homes, the VA. So again, our ability to be able to collaborate and take the lead from the Spark Hub was huge. So, you know, moving on, some of the folks that we were actually able to help, Jay can actually go into that.
Okay. So, you know, having Jay sort of tee up the ball and get some of this product going, also started to identify folks who were trying to help. You know, again, you know, you really don't know who you're trying to help until the pandemic hits, and all of a sudden we say we don't have stuff. So that's where this came from. But out of this, we helped over 6 major hospitals, 16 first responding agencies. In other words, that goes from county fire departments all the way to state law enforcement that were responding as well. 6 nursing and living living centers. Now, you guys know when you look at a lot of the deaths that were happening early on, a lot of those deaths were happening in nursing homes and assisted living centers up in the Northeast. We saw that as we needed to get ahead of that. So we started reaching out to our local people that were providing that and said, hey, we have some resources for you. At that point, everybody was scrambling for PPEs. Everybody was. And so you couldn't get it. So what we were able to do was start looking at that. You know, we have another group that people don't think about is your prison population and the guards that service them. You know, reaching into those, again, everybody's scrambling for PPEs. You just cannot imagine the calls that we're getting. And then finally, as we start to transition in, now we're getting into where the school districts. We provided a lot of PPE stuff for the school districts, and we've seen a lot of the transition going from the 3D printed parts to the mass production of injection molded parts, of being able to service. Initially, it was 600 to 700 pieces of face shields. Now we're at thousands of face shields because of how you transition from 3D printing, which is the prototyping model, into small run production, then into true manufacturing, which is injection molding and how you do that. And again, this is just a sample list of a lot of the people that we helped across the way, and there's been many more since this list was created about how that was to work. Now, in doing this, 3D printing was a major part of what we were doing. It was not the only thing we were doing. You know, we talked about the initial push on the 3D printed mask, which we started originally with Jay and Mercer, and in doing that, we actually produced over 7,000 face shields that included about 1,000 3D printed molded brackets like this. And then also we went into injection molding and did another 7,000 or 6,000 in that revenue or that area. We also did gowns. We did over 11,000 gowns that we produced and delivered. Again, it's about the Innovation Center is not just one thing, it's a lot of things. And what's interesting is once you get that community going, they want to know how they can solve a problem. And really, truly, that's what this is. We had, you know, over 45 community volunteers show up and start doing cutting gowns that we're providing to the medical area. Matter of fact, 461st had a group of airmen come in and actually do that as well and bring it over to the facility. And the other thing that you know, all of a sudden, everywhere the first responders were having to wear masks all the time, like sort of we are now, right? Well, what they were seeing is initially they were getting cuts behind their ears because of that pressure. So we initially went into a laser cutting model, and then also a 3D model of a tension strip that took that pressure off the back of the ear. So you're being innovative in your community at all the times. It just didn't have to do with 3D printing, but what's interesting is the starting point for a lot of this stuff is 3D printing. Is how do you prototype something very quickly? And 3D printing is just that model that allows you to do that. So again, you're talking about 26,000 pieces of PPE that were provided to the first responders, healthcare providers, and now the school systems of our local community. So how do you get this ball rolling? So obviously Jay called us. You know, I'm not gonna lie to you. I knew as soon as we got into this thing, we were going to be neck deep into it. So I tried to keep Firestarter out of it as long as we could. So in February, I saw the need coming. Matter of fact, we're part of a national makers web group, and on top of being in with the National Fab Lab Foundation. We saw it coming. We saw it coming when it was in Australia. We saw it when it was in Italy, because all of a sudden these maker groups were saying, hey, we need these PPEs. This is what we're producing. This is what we're doing. And you're seeing it rolling across the world on its way to us. So being the national or international foothold of makers allows you to see trends coming, and it was coming very rapidly to us. And the other side about it is you don't want to reinvent the wheel. A lot of times you're looking for things that are already out there being used and proven, and how do you deliver those? And so we got a call from Jay and said, hey, we're working on something with Mercer. We're going to donate this. Do you want to get involved? And by that point, I was like, okay, I can't turn it down. I got to go. And so we got everything ramped up and going. So the first thing you do is you tend to put out there and come up with a common design, because at the end of the day, everybody's got to be doing the same thing, or you'll never get to mass production. So what we ended up doing is say, okay, we need to do a grassroots call. So the first part of the event today was all about celestial dreaming and being. This is all about grassroots, in the dirt, in the mud, get it done type stuff. How do you get it done? You gather people. And so what we ended up doing is doing an all call on our Facebook page of anybody and everybody that had a 3D printer that wanted to help produce it. What we're going to do is we're going to put a file out there and sort of govern the process. Well, the next step with that, though, is you got to get leaders. And your volunteers are your number one resources, right? At least for a 501c3 like for us. So we actually came up with two guys here that are local guys. That they're both ex-military, and they are 3D printing enthusiasts. And so they said, okay, we can do this. And what I did, being a good manager that I am, I gave them what we were doing and said, here, run with it. Don't let me be the bottleneck. If you're waiting on me, we're backing up. And so these two guys really set up the whole process for us in moving forward. What they ended up doing is setting up our communications. So they vetted the product that we were doing when we set it on a PERSA design, and these guys were using PERSA computers or 3D printers. And so we also set it up on a version of their 3D printed bracket. And in doing that, these guys were vetting the design, vetting the product that we were printing with, because not all products are the same. You know, you can get one filament that has a bad design or has a bad result, and if you find the correct filament, all of a sudden that turns that result completely around, and the product's so much better. So that's what these guys were going through at the very beginning, is because you're trying to vet the end result, which is everybody printing the same thing in the same quality. No matter if they're using a PERSA printer or a MakerBot or whatever else, you want them to be fulfilled that if they're going through the exercise, that you want them to have the output that is something that we can all sort of work with. And so that's what these guys really did. I mean, they through our Firestarter Fab Lab community, they set up a Slack page and did 3D printing, and it was nothing but 3D printing on projects. And you're talking about right now, they're talking about the different filaments they were using at that point. The next thing is you get the production going, and that's what you see here. You see, this is actually one of the guys that's 3D printing, and he's in the midst of doing it. Now we started with just those two to begin with, because in reality it's great if you kick it out to everybody, but it's really sometimes the wild west of misinformation if you don't really refine your message and your product. So we started off with these guys just doing the production, and at this point we were at 20 to 30 pieces. And this is our first run. If you notice, when you do this, every piece has got to be the same because it sets up for the next thing. 3D printing, the bracket is great, but then you have to get the face shield, you have to get the strap that goes to the back of it, you have to figure out how you're going to package it so it can be self-contained. And that's sort of what this was, but we wanted to collect the resources. This is collecting the resources needed to actually make that process work. So we found the 3D printers, we saw the design and made sure that it worked out right. So the next step is, what about the face shields? What about how are you going to find something plastic? Because at the time, everybody from everywhere was collecting any piece of plastic that could be a face shield. It was off the shelf. You could not go buy it from anywhere. So we ran across our friends at Georgia Tech who had got a donation from Coca-Cola. They had 1,800-pound rolls of PET up at their facility up in Atlanta. Through JVIZ and Georgia Tech Research Group, we were able to connect into that. We sent a tow truck up to go get it. One of our local heroes here in town, he went up and said, "What can I do to help you?" They said, "We need this product. We need 2 rolls of it brought down so we can start breaking it out." Well, once we got it down there, there's one thing, because 1,800-pound rolls, you just can't handle it with everything, right? So that's where we went into my group here at Flint, and we just had to have stuff that was spool-based. So we were able to put 1,800-pound rolls of spools on our equipment and start breaking it down. And we were actually able to break it down into about 80 to 100-pound rolls. And at that point, you can take that 80-pound roll, sit it in front of a laser cutter, and start the production of the face shield. And again, digital design, right? So we're doing the face shield exactly the same every time. Our holes in the same place, and then all of a sudden, these 4 holes on here, match up with 4 holes across the 3D printed model. Okay? So that's really where this whole process started, and sort of the iteration of how you stack everything together. Because again, you don't find a finished product. I mean, that's the end goal, right? If we're trying to give something to somebody where they're not having to do a whole lot at the end game to actually get it to actually be usable. So what we ended up doing is we had a drop-off box that a zero touch. If you guys remember at the time, it was about no interaction. I mean, that was the whole deal. So we did outside of our lab over there. We put boxes outside and had our crew of 8 3D printing gurus. That's what we call people that help us in our volunteer side of things. Producing 3D printed models or brackets and then coming in and dropping them off. And then we go through a quality control process If you guys see, this is the tension strip. Believe it or not, that is vinyl roofing. It's in the gutter area that we put on the laser and cut it to shape. It had enough elasticity to it, but also would not over stretch. That allowed us to use that as the tension strips in the back. So you had a quality control. At this point, you had the face shield at the top being it's already cut. You had the bracket, and then you had the tension strip, and then we came up with the process of delivering it through just. This was early on. We were doing bags that you get at the grocery store, but eventually we came up with a little more high-tech process in doing that. It actually looked a lot more professional. But in reality, this is what the end game was a face shield that people felt comfortable with using. Because again, we're trying to give them peace of mind of what we were doing, that they were safe and be able to provide that moving forward. So when you start to put face shields out in the community or gowns out in the community and other things out in the community, all of a sudden you have other people come to you and says, hey, can you do this? Can you do that? If you remember, especially here on base, there was a community group on base that were doing face masks. And they had the early on, they had the pleats in them. And they were doing them in hand because you couldn't find them anywhere. So they were sewing them out of anything they could get their hands on. Well, in doing that, there's two things that happens. One thing that happened is you couldn't find the material. The second thing is you couldn't find the elastic for the ear bands. So going back old school, but new school sort of helping that, is all of a sudden you had about 100 sewers in our community that were sewing things that are called bias tape. That is the little tie strips that go in the back. The old school medical boobies that you'd see, everything was tied. Nothing was elastic. It was all tied. Well, in doing that, these are bias tape strips. So you put a material through this and it curls it and they can sew it. All of a sudden it speeds up the process because it's got one constant pull and you pull it, sew it, sew it, and it's a constant process. So it speeds up the process. And then the other thing was, not every pleat maker is precise and exact and skilled at it. So they asked, well, could we find a pleat maker that would make things standardized? Again, when you start doing production, it's about standardized. Everybody wants the same thing to look the same way. So we actually found both of these products open source, online, and printed them in mass. So that we had, like I said, over 100 in the area here. But if you talk about Middle Georgia as a whole, we had about 500 people sewing masks and turning those into pieces that the first responders were using. The base was using, training on base was being used in doing that. And so this is sort of what happens is you have a constant flow of, okay, they use 3D printing, they use the resources, innovation to make product. What can you do? This is our issue. And then obviously when you're in an innovative environment, people want to solve problems. So again, the community can rally together, or the innovative community rally together to find a solution for that. Well, jump 3 months ahead of that, 4 months ahead of that. School's getting ready to roll back in. Middle school band directors start to wonder out, how in the world can I have, normally I have a group of kids, and they'll go in and they'll test the instrument, and then they'll take the mouthpiece off, we'll put it in some liquid over here and wash it all off, and the next kid comes in, he'll put a reed into it and test the instrument, and they're going to pick and choose the instruments they're going to use by sampling the product and blowing on the instruments. Well, in this day and time, you couldn't do that. There was no way for them to do that in their normal setting. So we had a local band director come to us and said, hey, all my middle school bands, this is our time. If we don't get kids now, we are never going to get kids. It's hard to get them into the system. So we need to continue the way we would do business. Can you help us? He was able to locate 3D printed models, open source, of all of the wind and brass instruments that they needed to do testing for their kids. He brought those files to us by gurus, went through the files, did a couple of prints, and cleaned up the files so they were usable. We actually brought him in and he would put a reed in one and we'd blow into it and check and make sure if it would work or not. And if it wouldn't work, we would change it. So we were prototyping that model. And then once we got to the next stage, we actually started producing them. So we actually produced over 600 mouthpieces for the middle school bands here, directors here in Middle Georgia Houston County, so that they could continue the process of engaging these kids in extracurricular and in art driven work outside or inside the normal school protocol. So again, that's another thing that when you start the innovative model of 3D printing and just purely answering and solving people's problems, you get to be known for that. And engaging your gurus and your people in 3D printing, their expertise, and allowing them to connect the dots for you, that's really, truly what the great ideas and processes are for this. So a little bit of lessons learned.
So, again, this goes back to, while we're talking about 3D printing, this goes back to innovation, right? And it goes back to collaboration. So, while Jay Biscard and his folks were, no pun intended, the spark that started us off here, with the Spark Hub, to be able to turn to community partners, especially like Firestarter Fab Lab, when you're talking about, next thing you know, they've become the hub, right? And we're all spokes off that hub that are all putting into that effort. Because if we didn't have that collection point with those no touch collection points like Firestarter Fab Lab, if Jay is not collaborating with folks, how are we getting those pieces? They're not getting on base. So all your folks that are out there, your universities, all your innovation centers, your private citizens that are actually doing this at home, where are they going to get this stuff to? Again, it comes down to collaboration to be able to get those in and get them all distributed. So again, we've got some lessons learned that, after we're on the back end of this, as we start to come out of this, but going into this, and we were deep in the middle of trying to figure out how we push forward here and how we collaborate and who does what. But I will tell you that, it says it right here, creating a community where everyone has input but agrees to work together, right? Again, that goes back towards everyone wanting to try to do their part, but focusing their energy. And that was a great thing that the Spark Hub and the Firestarter Fab Lab did when they were like, okay, we need you to make X, Y, and Z so that we can get those collected, we can get them distributed.
Well, one thing about that. So innovators are notoriously rabbit hole people, notoriously. They'll solve a problem, and in their mind, once that problem solved, man, I'm on to the next problem. But in reality, the thing is you want to collect those people that solve those problems, but also you want to steer them in the direction of, hey, not only do we have to solve the problem, but we have to provide the deliverables too. And so in doing that, that's a big part of it, is give them the upfront feedback or the ability to feedback. But really, once we start down the road, let's everybody agree that, yes, our model may not be the best, but at this point, everybody's doing the same model, so it's quick to the fight, right? And so that's the people that bring the most usually win. And that's what we were trying to do, is bring the most.
And that actually plays into, input from our producers. So again, those gurus, everybody has a different way to do it. Doesn't make it better or worse, just different ways. What was awesome about being able to crowdsource how we did this was you would have somebody come in and go, hey, I found out a way to stringlight this part. It was awesome. Because again, you're able to get it out, especially when patients were set up to get that information out. You're able to actually return things. So one of the biggest things, especially for Firestarter Fab Lab, not so much for Spark Hub, but when we talk donations, when we talk trying to figure out, all right, how are we going to get resources, supplies, logistics support into places like Firestarter Fab Lab, how do we do that, right? So again, the ability to, you had organizations like the International Rotary that came in to wanted to donate cash, instead donated 3D printers. Because we got in on this early enough, we were able to actually get out there and get printers before they went on back orders for 4 to 8 weeks, which that definitely put us at a disadvantage as we tried to expand the operation. But we had enough between all of our innovation centers, between Spark Hub, between Firestarter Fab Lab, and again, those community partners out there actually doing these things. But again, it did highlight, okay, how do we do this in the future? How do we streamline this? How do we actually help Firestarter quick? So,
yeah. So the other thing about dealing with donations, because people give you cash, but also, in just the thing, again, trying to bring most to the fight is in reality, at some point, you're going to have products that people donating to you, and you're going to have products that are finished, ready to go out. And the thing is where are you storing both the raw product and the finished product? Where are they being stored at? Because imagine in a Spark Hub location, which is, probably 3,000 square feet, that if you have a bunch of boxes come in or a bunch of product come in, guess what? Your floor space goes away really quickly. And so trying to figure out where you're storing stuff, but also keeping that flow going. It's great to do just-in-time inventory control when you're doing a mass pandemic answer, but that's not the way it happens. It usually comes in a big 18-wheeler, and it says, okay, how much of this do you need? And at that point, you say, everything I can store wherever I can get it, so you just start hoarding it. Because in reality, for us, we not only were an answer here locally, we were not only lasering face shields here locally, we were sending that product to Columbus. We were sending that product to small towns that had lasers in high schools that wanted to help as well. So you want to gather as much as you can and build that network of people that are trying to do the same thing, be it 3D printing or at some point we were trying to chase filament, and where do you get filament to do this? So that's a big thing that you really sort of have to think about is once you do an all-call and you start to collect this stuff, it is a manufacturing process. And part of manufacturing is storing your supplies, both the raw material and the finished product, and doing that. So that was a really big deal for us. And this is really the lessons learned that we had in moving forward. And then I guess the final part was delivering. That was probably one of the most rewarding parts of this. We did, if you guys remember that long list of people that we donated to, very few of those were shipped. A lot of them were hand delivered because of needing to get it to the right person at the right time in doing that. And one of the most rewarding things I can tell you is when you roll up to the Veterans Center, Veterans Hospital in Atlanta, that is in the epicenter of Atlanta's COVID-19 outbreak, and roll up out there with 3,000 gowns and 500 face shields and another 1,000 face masks, and they're sitting there saying, we can use this today, and you unload your truck and you're knowing it's getting into the fight for them that moment. There's nothing more rewarding than that. And the reason why I'm telling you guys this is because Viz was not able to be there. You weren't able to be there that day. And there's a lot of things that the Spark Hub was not able to do because there's so much that has to be separated between what happens inside the fence line and what happens outside the fence line. But I can tell you, the energy provided through Viz and the connections of what's interesting is it's amazing. When you're in the military and you're innovative, there's a lot of people who want to do work with you, and you create these connection points that don't necessarily always help you in the military, but just a little bit of push outside the fence and connecting the dots outside the fence becomes this huge rewarding experience of true production. And that's the biggest thing that I would like to commend Viz and his group here on base about, is that taking that energy, because you spend a lot of energy, but taking that energy and then not only keeping it to yourself, but throwing it outside the fence line and letting us sort of rally around that and create the deliverables that we were able to create.
And to echo that, Viz and the team here live by the adage of it's incredible what you can get done when you don't care who gets the credit. So, again, being able to work with folks like that, huge. So, thank you.
So one last little video, and this is sort of about midway through our process and was telling our story. Now, what's interesting about this is Firestar spent about $28,000 on raw materials. And when we started this, we had about $20,000 in the bank. And so we went past our funds really quickly. But guess what? When we opened back up as a fire starter lab, which we did in May, we had to have back our cash flow back to operate as a business, as a community business. And so we had to recoup that. So we have to tell you, when you do a nonprofit and when you do events like this, you have to find a way to rally people around you to gain funds to help pay for what you're doing. Goodwill goes a long ways, but it doesn't pay the bills. And paying the bills allows you to bring it to the fight, and that's sort of what this leads into.
Nikhil, as the need for personal protective equipment increases, some healthcare workers might find themselves without critical pieces of that equipment. Well, Firestarter Fab Lab in Houston County decided to fill in that gap and give those on the front lines the tools they need.
Our medical groups to battle this pandemic. I mean, they're in a war and they need tools.
Jay Flesher with Firestarter Fab Lab, a nonprofit innovation lab, says when he was made aware of the need for personal protective equipment like face shields, he knew the lab could answer the call for help from those on the front line.
We're sitting here at the Houston County Career Academy with $300,000 worth of equipment and volunteers that know how to run it.
Volunteers at the lab, along with community partners, started making face shield brackets along with mask tension strips to ensure healthcare workers had the safety and comfort they deserved while fighting COVID-19.
We'll put a face shield on somebody that needs it in a critical situation, and it will save them or actually save the PPEs that they're using that are really, truly critical.
Flesher says it isn't only about the physical health of those on the front lines, but their mental health as well.
If we can give them a little bit of security, a tool that they would not normally have because it's not available, then I think we've done our job.
So far, they've made 6,000 tension strips and 350 face shields with the help of volunteers and donations. But Flesher encourages the 3D printing community to do more.
With us and find out what you can be printing on your tool, on your manufacturing tool, and then get your piece of equipment into the fight with us.
Flesher tells me coming together as a community right now is essential, and it tells our healthcare workers that they aren't alone.
So that was, if you guys noticed, it was during the pandemic, so the haircut was sort of a mess, and I decided to go ahead and shave as well. So it was sort of scraggly and that, and you know, I get blamed for talking a little too much sometimes, so they almost muted me all the way on the video side of things. So, but in doing that, you also have to do presentations. You know, even though public speaking is not necessarily my thing, it's sort of an act for me. I'll get up here and just do what I need to do. But whenever you do a presentation, you inform people about what you're doing. If you're passionate about it, it works. But every time you do it, at the end of it, give them a way to act. Give them a way to engage. And so whenever you're doing something that's along these same lines, man, and you're telling people what you're doing and why you're doing it, give them something at the end that they can make an impact on what you're doing as well. So thank you for you guys' time. Javiz, thank you so much.
Thanks for joining us today. Thank you. Gary and Jay, keeping up the tradition over here because it's a 3D print workshop. I'd like to present you with this token. We'll stay 6 feet apart there. There you go. And thanks for joining us. And they really, truly bring the story here in this kind of local community. I mean, we can work with folks outside the fence. There are ways to break through those barriers. You know, in COVID-19, really, everybody was biased towards one solution, and that was getting protective equipment to folks that are on the front lines and to maybe some of your family and friends, you know. So that is the true power of collaboration. And to you folks out there with the Spark Cells, build that ecosystem around your base and connect with your folks outside the fence. All right. Thank you so much. Thanks for
I was able to work with transitioning military in your Spark Hub through a Department of Defense grant, through the Office of Economic Adjustment, through Middle Georgia Regional Commission. So this was originally created for them. And Jay shared a little bit about some of their success stories. One of our success stories at Spark Macon was Marion Systems. This was a spin up that came out of Spark Macon. Garrett Sisk that founded Marion Systems, he is an engineer in the area and builds 3D printers. So over the past 3 years, I've got to see the evolution of 3D printing.
3D printing.
Oops, and go through some of the just the challenges. And I wanted to give you some overall feedback. I don't know what your background is, but I hope to provide you some content and some more real world applications and get you 3D printing with the flowchart.
Technology is already changing the way we produce objects, from tools and toys to clothing and even body parts. 3D printing is part of a process known as additive manufacturing, where an object is created by adding material layer by layer. Additive manufacturing allows designers to create complex parts for machines, airplanes, and cars at a fraction of the cost and time of standard means like forging, molding, and sculpting. Now, smaller, consumer-friendly 3D printers are bringing additive manufacturing to homes and businesses. The first step in 3D printing is to create a blueprint of the object you want to print. You can use modeling software like Blender to create your own designs, or you can visit websites like Thingiverse or Shapeways to find objects other users have 3D modeled. Once you have a finished design, it's time to send it to the printer. Some printers, like the MakerBot Replicator 2, have renewable bioplastic spooled in the back of the device, almost like a string. When the printer receives the data, it pulls the material through a tube, melts it, and deposits it to the plate where it instantly cools. As you can see, the 3D object is created through layering, where the printer will add one layer of the object at a time until you have a fully formed structure. The most common material used in 3D printing is plastic, but the use of some other materials allow for the creation of some pretty amazing products beyond simple tools and toys. 3D printing food is becoming very popular, and additive manufacturing has allowed for the creation of some pretty intricate treats. In the medical world, doctors are testing biomaterials for regenerative medicine. By using a patient's cells, doctors could 3D print small body parts like ears and noses. Some surgeons have even tested 3D printed organs for transplants. Recently, giant 3D printers in China printed 10 houses in just one day and at a cost of less than $5,000 per house, proving just how cost and time efficient 3D printing can be.
Okay, so that's a little overview of 3D printing. And I wanted to make sure to stress that it's very important to read your manual and at least understand if you're breezing through your manual, make sure you know your components of the 3D printer, make sure that you understand how those components work together, and then look at your FAQs, because if you have a question, it's probably in the frequently asked questions section of your handbook or your manual. And then also Google. The first thing that you Google might not be the best answer, but there's a lot of content there, so you'll probably find your answer. Somebody might have already done a YouTube video on some of the models that you're familiar or that you're working with. So let's go ahead and go through 3D printing flowchart. So if you want to 3D print something, first you have to decide what you want to 3D print, and you have options. So your first option is going to be to go to a database and grab something. Your next option, you could go to a database, grab something and modify it if you want to personalize it. You can scan it in, or you can just go ahead and start creating yourself and 3D model it. So the first thing for the 3D printing flowchart, you've got to have an STL. You've got to have something that you want to print. So the first thing is decide what model you want. So if you want to grab something from a database like Thingiverse, you just go ahead, go up to the search bar, put something in there, search for it, and there's a number of items that are already have been pre-modeled. My Mini Factory is another great database to go ahead and search for models that somebody has already added to the database. So you can just download that. The second one, pre-made and modified. I did a lot of both of these. So I like to design hydroponic systems, and I would find that I would spend $37 at Lowe's just trying to connect from one area to the other. But when I started to 3D model, the first thing I started to model was couplings, and I could spend like 36 cents on PLA filament versus a ton of different connections that I would have to connect together just to make one connection from Lowe's or Home Depot. So that's a application that I used. If you want to personalize something, I loved making nameplates for people. Here's a really fun card box to give people. So if you want to grab something from a database and then personalize it, 3D model it, that's always an option too. The next option, scanning. So you can, here's a variation of scanning from small.
The magic of the MakerBot Digitizer desktop 3D scanner. With this piece of equipment, you can scan an object up to 8 inches in diameter and 8 inches tall in under 10 minutes and end up with a 3D model that you can send directly to your 3D printer. Let me show you how it works. So I'm going to go over to Makerware for Digitizer. This is an app that's free from MakerBot, and it's responsible for talking to the digitizer, acquiring and making sense of the data. When we launch a new scan, all we really need to do is describe how light or dark the object is. This is going to help the scanner comprehend the image data that's coming from the sensor. We can go light, medium, or dark. In this case, I have a light object, and then all we need to do is click Start Scan. In a few moments, the magic will start to happen. So our scan completed. Let's take a look at Makerware to see what we came up with. So you can see here I have a nice model of my monster head, but there's one thing that I'm seeing here that's a little bit of an issue. My monster head has kind of a concave feature on top, and the lasers can't really see down into the cavity very well, so I'm not getting really the best level of detail. Now we can take advantage of what's called a multi-scan. When we click on Start Multi-Scan in Makerware, we're going to be able to reposition the object. So I'm going to lay the monster head on its back and then click on Start Multi-Scan. And what this is going to do is it's now going to rescan the object from a different angle. It's going to see into all the areas that it couldn't see to before and reconcile the two 3D models together to have a better level of information and data. Let's see what happens. All right, so now that we've scanned from another angle, let's see what we've come up with. So I've got the multi-scan model open here in Makerware, and it's actually looking a lot better. The detail on the indented portion of this monster head is looking fully detailed, and it's great. So we could actually add additional scans, but I'm going to go with 2 here. I saved this off as an STL and have it open over here in the 3D Builder app. Now we can easily send this to our 3D printer using the built-in printing support. So we're just going to go ahead and go with the MakerBot Replicator 2. We're going to use all the default options. That's going to work great. Hit print, and boom, it's going to print out a copy of my monster head. Well, there we go. With the MakerBot Digitizer and the MakerBot Replicator 2 attached to my Windows 8.1 PC, I can make almost anything. If you want to know more about the MakerBot Digitizer, go to makerbot.com. If you want to see more awesome 3D printing action, please visit the Extreme Windows blog. Thanks.
Okay, so that's scanning kind of on a small scale. at Spark Macon, we have a sense scanner. So you can see right here that he's scanning a bust and creating a point cloud right around here. And the point cloud actually creates the digital image that you see there on the screen. So a sense scanner is a little bit of a larger scanner. It can take in more area. Right here, you can see a full scan of somebody. So you can scale that to size too, or you can, scale it down and get a smaller model. And then the next one, Canvas, is a industrial application, and it is a lot larger, and it's used in architecture and then also for building design as well.
Canvas is a groundbreaking new application that allows you to capture a scale-accurate 3D model of your home in minutes, all on an iPad. Here's how it works. First, attach a structure sensor to your iPad and launch the Canvas app. Next, start scanning. Canvas captures thousands of measurements per second and combines them into a single 3D model you can use instantly. You don't have to anticipate every measurement or view that you'll need, because with the 3D model, you'll have all of them.
The great thing about Canvas for us is that we can take any of our employees, send them out to a site, have them capture the whole thing, and we have all the information we need without error.
A raw 3D model is powerful, but if you want to make changes using professional tools, you'll need a simplified, editable CAD file. That's why we built a new, first-of-its-kind service right into Canvas. We call it Scan to CAD, and it converts your raw 3D model into CAD within 48 hours.
When I got my first CAD file back, I really wasn't sure what to expect. And when I saw the file, I couldn't believe it. It was so accurate, so thought out. Everything was in perfect layers. I can rely on Canvas and Structure Sensor to provide me with more information than my brain would even remember to take a look at.
Clients of all levels want to see 3D modeling. Now that we have Canvas, we can create that same level of project and of presentation for all of our clients. I think it would pay for itself in one project.
To make real-time 3D mapping possible on the iPad, we had to create new hardware and new software. First, we created the structure sensor, giving mobile devices scale-accurate depth sensing. Next, we're introducing a new 120-degree wide vision lens, which means you'll experience our most stable motion tracking yet. And most importantly, we've upgraded our mapping algorithms. We've gone from enabling you to scan objects to now allowing you to capture entire spaces. For the first time, it's actually easy to turn a physical space into data. Space is the new digital asset that you can store and bring with you wherever you go. Canvas is available now at canvas.io and on the App Store. And we can't wait to see what you do.
Okay, so those are three different examples of scanning. So we've talked about in order to 3D print, you have to have a model that you want to 3D print. You can grab it from a database, you can scan it in, or you can model it yourself. So if you want to get started with modeling, or you've been modeling in the past, here's a review of some of the different 3D modeling softwares. Tinkercad is really fun to start out with. It's super user-friendly, very easy to kind of navigate. We had a community leader at Spark Macon, Michael Rosario, who was my mentor and principal software engineer at Mercer Engineering Research Center. And we were able to do a fun workshop together at the Museum of Aviation there. We had students, a range of middle school students come in, and they would model something in Tinkercad and then download it into Minecraft, which was fun. Also in Minecraft, using MC Edit, you can create something in Minecraft and you can print it. So that's a lot of fun if you're getting started with Tinkercad. More intermediate softwares, Blender. Blender is if you're interested in animation, you want to 3D model a character and animate it. Rhino is more for architectural design. Onshape I used a lot with parts design. I would have people come into the makerspace and they would say, I broke this on my Jeep, but I can't find the part anywhere. Is there any way that you could 3D print it? So we would go ahead and we would generally 3D print in ABS, make any changes if we needed to 3D model wise. so that they could have that, and Onshape is one of the applications that I use for that. And then of course, SolidWorks industrial level for engineering if you are not working with open source. So that is, those are, oops, let me get back to my spot. So if you are 3D printing, first and foremost with the flow chart, you've got to have, you know, something to print. So whether you're getting it from a database, whether you are scanning it in, or whether you are 3D modeling it yourself, those are your options to get a .stl or a .obj file. So step one, make sure that you save as a .stl or a .obj file. Here's kind of an example of that right here. This is Fusion 360. If you're familiar with that, you just save it as a .stl. And then you're gonna, of course, want to choose your filament, put your filament in. Here's a range of filaments. I mainly used ABS, PLA. We had TPU at the Career Academy, but there's a wide range of filaments to choose from. So after you have your model and you put your filament in, the next thing you got to do is make sure that you use a slicing software. So the slicing software is going to turn your 3D model into G-code. Cura is one example of a slicing software. And all that does is it just uses coordinate access to go ahead and lay down the filament. Here's a really good example here of G-code. Also, G-code is short for geometric code. You can tell that right here, the filament is laid down in layers. So when you're printing a 3D model, what's happening is it's being sliced into layers, and when it's sliced into the layers, it's turned into G-code. And then from there, after you have your G-code, that's what you're going to send to your 3D printer via USB cable, SD card, Wi-Fi. You can send that G-code to your 3D printer in a number of ways. Then after you have your G-code sent to your 3D printer, your firmware is going to interpret that G-code and go ahead and print. So I'm familiar with a range of 3D printers. Jay said that you guys had a TAS there. I developed the curriculum, the training on the Pressa, and at the Career Academy, I was able to use Tier Time, which I really enjoyed because it was all enclosed. Some of the problems that we had when we started 3D printing were, of course, the extruder getting clogged and airflow issues. So having the Tier Time, having something enclosed was really nice because I didn't have to worry about any kind of airflow messing up the printing anymore. My number one tip is if you're 3D printing and something goes wrong, don't freak out and turn it off, because that's how extruders get clogged the easiest. And then also a little brief about going back to the manual. If you know your components and you know how your components work together and you read your FAQs, then it's really easy to troubleshoot through these. You can see just some of the main pieces here, LCD screen. You've got your motors that are going to control your axes. You've got your heated bed. Most of the parts and components on all 3D printers are the same. They're just arranged differently. So if you know your components and you know how they work together and you understand how your X and Y axes are moving, your Z axis, then it's a lot easier to navigate and troubleshoot through those problems. Go ahead and Google if you have an issue, of course, and then look at those FAQs in your manual and you should be able to figure it out. You have an amazing network there in the Warner Robins area, so I'm sure that if you follow all those avenues and you need help, you'll be able to find someone. Here's a really fun challenge that I did with some of my students at the Career Academy, 3D Model Trophy Challenge. Students chose their own 3D modeling software. I gave them some parameters that they could operate within, and then they just created a trophy and the winner got to 3D print. So that's kind of just a brief overview, and I am a huge fan of innovation. I love to stay on the cutting edge of technology, and I just kind of wanted to leave you with the big picture. One of the things that I love about 3D printing and additive manufacturing is it's changing the way that we live. And I urge you to think about how long will it be before we are modeling and printing our own homes.
And thank you, Adrian. Thanks for sharing that with us today. And thanks for giving us a brief overview on 3D printing. I wish I can give you a coin in person, but we have a 3D coin, printed coin for you, and I'll make sure that we get it over to you in Colorado. Does anybody have any questions for Adrian joining us today? All right, Adrian, thank you so much.
Thank you, Jay. Have a great day.
All right, take care. Okay, I think we have our presenters. Hello, can you hear us, Laura? Enjoy
Yes.
Face Andrews?
We can hear you. Just
Perfect. All right, yeah, we'll just jump right in. So we had a 3D print overview, and now everybody's interested about scanning and would like to dive deep into scanning. So over to you guys.
Sweet. Yeah. Well, thank you for bringing us onto this this platform. First of all, it's really great that we can kind of talk to everybody and just share our knowledge with you guys and kind of get you guys on the same page as us. So for starters, we are the Joint Base Andrews Spark Cell. My name is Andy, and this is Hi, I'm Laura. Like the hurricane, and we are about to blow over all this stuff. So just for starters, we'll go ahead and introduce everyone real quick. So this is Jacko. He's the head honcho of the Spark Cell over here, as well as Mr. Zimmerman. We've got Rod here as well. We make up the Spark Cell team over here. We're going to talk to you guys a little bit about 3D scanning and what we do with it. So aside from everything that you guys saw, there's going to be a little bit of a lag. I'll be asking you guys questions. Who can tell me what 3D scanning is used for typically, like in the real world? Anyone?
Reverse engineering, somebody said.
Reverse engineering, cool. And that's a really high-tech thing. Let's go a little bit more surface level. How about gaming? So when it comes to gaming, a lot of the characters get 3D scanned. Also, one thing that everybody does use is Google Earth. So when you go on Google Earth or Google Maps and you do Street View, or you do like the overhead look where you're looking at the Earth and you can zoom in onto buildings, it's all done via 3D scanning. So those are just a couple of the platforms that 3D scanning is used for. Now, for us specifically, we have what's called an Artec Leo. This is a scanner that we use in-house, and I'm gonna move this down a little more. And this scanner is pretty awesome. It takes about 80 frames per second, and you could get some pretty good detail items with this. Now, our level of expertise with the 3D scanning is still pretty beginner to intermediate, but it seems like every day we're still learning quite a bit with this stuff. So what did we use 3D scanning for? And that's a good question. I'm glad you guys asked. So with us, when COVID first started, what we did is we started the mask initiative. So in-house, we started prototyping maps. We actually went online. We were able to find different prototypes, different masks that people were using, and we started making our own modifications to them. If you look over here, there's plenty of different types of masks that we've been working with, including our Chipotle sponsored mask over here. So it seemed to have been working out pretty well. However, one thing that we did learn is that although these are generic masks that we were able to make work for a majority of the people, not everybody has the same facial structure. So what we ended up doing with that is we ended up scanning people's faces with this scanner. So we ended up putting people up against the wall in our Spark cell. We were able to do a 3D scan of their face, and we were able to put them on our CAD software. And what we were able to do was scan their face and then get a mask that can fit specifically for that individual. So this here's Chief Wright. Just a couple months ago, he came by and we were able to scan his face and we made a mask that fit specifically for him. It's pretty awesome with the capabilities that we have with it. So there we go. And then we will go ahead and move his face onto it. And then we can fit all this stuff specifically for him. So it's a pretty cool thing. When it comes to 3D scanning, we're trying to branch out to other units across the base to see what type of things that we can scan within their units, to see if we can replicate it, reproduce it, and potentially make our own versions of it. So with me, I'm into cars. Do I have any car guys over here? Or women? Anyone into cars? So when it comes to cars, aeromotive parts, so aero parts, engine parts, all these different aftermarket parts that you're getting, a lot of these companies utilize CAD programs to create these parts for their cars. It's not like they're chiseling things out and they're recreating the wheel every time they make it. They actually get the 3D models of everything and they're able to create their products with those 3D models. So for me, my project over here has been working on my own car. So what I went ahead and did, I went out and I was able to scan my own car. So I have a Subaru STI, and I was able to scan my car and put it in a form of a 3D image. And my overall goal with this is to create my own aero parts for this and really just see what I can do as far as producing my own parts, which, you know, could cut down on costs, on labor, and stuff like this really works on the outside. And if you could score a job doing this on the outside, I'm sure it'd be great. I don't know about working Mars projects, but at least for surface level things, we could do some pretty big things with this. In-house, it's pretty much the capabilities. Actually, if we come over here, we've got another scanner and we call it a joystick, but it has
a helicopter cyclic.
Cyclic, there we go. And what we were able to do is find a plane for this, and we were able to scan this product and throw it onto our program. And we were able to create a whole new version of this. And what we can do by that is say if this thing breaks, we're able to 3D print a whole new one and just replace the parts that are broken. So overall, that's what we're trying to do. That's the overall goal. See if we can create things, and if things are broken, see if we can fix them. So far, we've worked with Air Force One with working on different projects for them, for their planes. We've been doing this and just various things in-house, but I guess the biggest thing that we've been working on has been the mask. So does anybody have any questions? Actually, we may have some more info about it. If Mr. Zimmerman.
Sure. So you've kind of seen what the team has been doing primarily for COVID, as well as some of the other base-wide projects. So let's go back over here real quick, and we're going to show you how we started out with all of this. This is a Peel 3D scanner. So it's made in Canada. And when we first started the Spark Cell, we thought, hey, we want to be able to have a 3D scanning capability. And my whole goal when we first started this was to say, hey, you know, Iron Man can do it. Why can't the Air Force? So we wanted to be able to 3D scan stuff, use these smart tables and smart boards to take these projects and put them all up all over the place and be able to, you know, create solutions for people that come to us with the problems. So this was really cool, but it needs to be tethered to a computer. It needs to be tethered to a power source. The amount of detail that you get out of it isn't quite right. So when we said, and that was good for training. So if anybody's considering that, it's about $5,000 or $6,000 or so like that. And it's good for training, and it comes with its own software so you can play around with it. So then we upgraded to the Artec Leo. And this one is a handheld. It's got its own lithium battery, so you can actually take it out outside. It's useful if it's really sunny to have an umbrella or something like that. But you can take it outside and, like Sergeant Renteria was saying, scan your car or whatever. But we actually bought this for a more useful purpose than just with inside the spark cell. This is actually a base-wide, if not regional, asset. It's quite expensive, so you don't want to drop it. But because it's, you can take it autonomously anywhere you want, and on the back side, it has its own processing and software included. So you can actually process a whole 3D scan in your handheld device. So when we took this to the 89th MXG, the maintenance group that works on the President's aircraft and all the VIP aircraft, we asked them, hey, would this be something useful for you? And they said, absolutely, because right now what they have to do, if there's a part that needs to be replaced, whether it's the president's wastebasket or, a rail that, the president uses to go up the aircraft or whatever, instead of having to remove that and effectively down the aircraft for a certain period of time while they take that back, scan it in their own antiquated scanning tool, they can actually take this on board, scan the not working part in place, leave it still there because it's still quite useful. It's not flight safety related. They'll take the scan back to their workshop, make the new parts, and then when they go back on the aircraft, they just go back with the new part, take the old one off, replace the new one, and it's minimal impact to the operations of the aircraft. One of the other things that we're thinking about using this for is going into facilities and being able to scan various aspects of the facilities. And we all know that there's over, 200,000 or 600,000 buildings, I can't remember, within DoD across the enterprise. So if you could take this and go and scan various bits and pieces and have them create an STL file that we can bring back to the Spark Cell and 3D print something, whether it's in plastic or nylon or titanium or something like that, that's going to be useful for those facility managers, because when you talk to them, they say it takes 6 to 8 weeks for special order parts to arrive, and then that part is not useful, or then they have to close off a section or something like that. So that's what we're taking a look at. So that's the Artec Leo. What we have purchased, we're still waiting on, is something called the Artec Ray, and that is a 360-degree scanner. Basically, it sits on a tripod, goes around in a circle, and as it does so, there's a LiDAR radar function that spins this way, and it captures an entire 3D image of wherever it is. I believe it's got 300 degrees scanning, vertical. So it basically can scan an entire inside of your room. And everything is in color. So the Artec Leo that I just showed you, the Artec Ray, whatever it scans, it also picks up the color using the wavelengths off of the LiDAR rays that it uses. So you can actually, and we had a demonstration here, and I highly recommend a demonstration from any company. The guys came in, put the Artec Ray out, and within 3 minutes, we had an entire 360-degree scan in color of our room on our smartboard. So when we had that demonstration, we invited security forces, we invited facility managers, and we invited aviation safety folks. Security forces loved it. They're like, if we have an incident, a traffic incident, or something else, we can take that out and we can create a whole 3D image of the incident area, which helps them when they're taking down their information or whatever and putting it all together. Now they can actually have a 3D model, because when that scan comes in, it goes straight into our software, and within minutes we've got a CAD ready 3D model of whatever we're taking an image of. The aviation safety folks love it, because if there's an aircraft mishap that happens, they can take that out to the site and create a, no kidding, 3D model of that aircraft mishap site. And I know there's some pilots in the room. I'm a retired Navy pilot, and I was also an aircraft safety officer and mishap investigator. Having that capability would be so beneficial, because as soon as the weather hits, a lot of that stuff either washes away, animals come in and start moving things around. The county police department or the county fire, people go in there and they start kicking things around, just trying to, put out fires and everything. But if you, no kidding, have a 3D model, you can actually start to build a better way to do that mishap investigation. So those are some of the things that 3D scanning can actually do for us. I appreciated the video that you guys had before showing the Apple iPad with the attachment. That's really cool as well, and that's kind of a low priced way of doing 3D scanning. But for some of the Air Force things that we're doing, using some of this technology is very much useful. And I think, Jay, you probably have done some of this scanning as well inside aircraft and engines and all that sort of stuff. That kind of shows the capability of those types of scanning. So that's kind of what we're looking at doing here. And at some point, we also want to do scanning to produce 3D environments, kind of like what Jay has done already, to help improve training on the base. And also with the, if this COVID environment, starts to take more shape, and if we continue to work in a dispersed environment, if we can create 3D environments, people can actually keep up with their training, which enhances readiness. So we're looking at that as a perspective to take as well. So right now, I think the team is ready to take any questions.
Chris, yeah, thanks for sharing that. Man, from Air Force One, I had no idea that you guys were scanning Air Force One and replicating. Did you mention garbage cans too? That's amazing. Also with crime scene and aircraft mishaps, a lot of folks don't think about things like that, and the power of 3D scanning. Also with virtual reality, and bringing 3D images and those type of objects into that environment. I did have a question, and probably some folks probably have the same question here, is as far as 3D scanning goes, when you bring these objects into the digital world, is there some cleaning involved, and is there some a refining, or does it look exactly like everything does in real life?
Yeah, that's a very good question. So when the objects do print, they come out decent, but they don't come out 100%. So it does take a little bit of polishing, a little bit of cleaning up to get it to look the way that you want it to. And there's a lot of trial and error that's involved with it as well, as far as measurements and getting the right shape and everything for it. But overall, it does come out pretty good, and we've been fortunate enough to have some pretty good guys here that are very knowledgeable in CAD. So they've been able to help out a ton.
Yeah, and I'll say too that when we had the PO3D system, it really taught our folks how to do 3D scanning cleanup, because the PO3D itself, or the 3D scanner itself, really created a lot of holes. So you're absolutely right, Jay. The Artec software, much better, a little bit more expensive. Okay, quite a bit more expensive, but the Artec software almost fills in all the holes for you automatically. Or if there's something that ends up in the final render, you can point at it and say, hey, this needs to be done this way, and click on it, and it'll fill it in for you. And if the fill-in isn't quite correct, you can actually tweak it very easily. So it all depends on what software you're looking for, and what sort of piece of equipment. And one thing I'll finally mention for purchasing these, we really need to be careful on where where these pieces of equipment are made. So like I mentioned, the PO3D scanner is made in Canada. The Artec Leo is made in Luxembourg. Those are both NATO countries, and they're not on the bad country list. Some of the other scanners that you may see that either come part and parcel with a 3D printer, you've got to check to see where they're made. The Einscans are made in Huangzhou, China, and they're made by a very large Chinese company. And that's something we probably want to avoid. So, any other questions?
Anybody have any questions in the crowd? Yes, we have a question.
Good afternoon.
I had a question on the masks themselves. I know you mostly use them for COVID masks, but have you pushed them towards like aircrew masks? I know going to flight school, a lot of issues with my mask. I have a very shaped nose. So if AFE folks had to hand grind nose pieces and masks for my pressure mask, I was wondering if there's any movement towards doing that with those folks.
Yeah, that's a great question. So we've actually started working on various masks. When this whole thing kicked off, we started using a bunch of different forms of the N95 masks. Some of them had canisters, some had different types of material that were built on them. We did have one flight mask at one point, and the main issue with that is there's a lot of silicone involved with the mask. And so we weren't able to print everything on them. However, there are pieces to those masks that we can print. And once we get that capability of actually printing silicone, then that'll just change the game altogether. One of the biggest challenges that we have seen is once we get a mask that works great, we still need to go through the process of getting it FDA approved. And that's one of the things that we're working with Bioenvironmental with to do the fit test. And once we can get all of those fit tests good and we can get a mask that fits securely and we get it to just be everything that we want it to be, we can start pushing them out. So as far as looking forward for us, we don't quite have any flight masks, I guess, in the works per se, but if we can get some of those parts that are on it, we can recreate those today if we wanted to. So, and that's a good idea. We should start doing that. Currently we have PLA, we print with PLA, ABS, we have wood filament, and we also just recently got some metal printers. And I could show you guys if you guys want to see them. So we use Raise 3D printers. A couple more down, but these things are awesome. With just the type of filaments that we use. We use Ultimakers over here, and the MakerBot, which is pretty good. But what we're looking forward to in the future, actually within the next couple of weeks, is we have a metal 3D printer that's coming in, and we're hoping to start printing a carbon fiber composite as well. So talk about expanding our capabilities. We can't wait to start trying new things.
And one thing I'll add to that is, good question about the flight mask. Unfortunately, the Innovation Center can actually print those types of things, but with our current acquisition process and testing and evaluation, anything that we print that's going to be used in operations, especially with medical or anything that you take in the air, it's probably going to have to go through. I'm a Navy guy, so it's probably going to have to go through the Air Force equivalent of NavAir to get approval, and that's going to take probably a lot longer than what you guys think about in needing, unless there's a way that higher level leadership can say this is an immediate requirement. Let's push it immediately and get it done. I know Dr. Roper and the Assistant Secretary of the Air Force for Acquisition, he's really looking hard at ways to increase the speed of getting the things that airmen need to them, going through entrepreneurial programs, or Small Business Innovation Research Fund, all of those things. So that might be a possibility, but good question regarding the flight mask.
Thanks, sir.
Thank you. You mentioned a good point there. There is a lot of 3D printing actually going on in the Air Force. A lot of 3D printing, and just nearby over here is an advanced technology training center, and they do actually 3D print aircraft parts. But you mentioned it there. There is actually a certain process, as far as the aircraft worthiness and certain things that things of this nature and solutions have to go through. But we're getting after it, and there's a lot of 3D printing I mentioned in the Air Force, and actually upcoming there is an Advanced Manufacturing Olympics hosted by the Rapid Sustainment Office, and actually one of our teams here at the Spark Cell is actually going to be competing against large and small businesses and universities. So you can see 3D printing taking off in the Air Force. And thanks so much for joining us today. We're just about running up on time, but Andy, Laura, and also Chris, I want to virtually give you guys a 3D printed coin. I'll make sure I get it over to Joint Base Andrews and send it to you guys. And your spark cell looks fantastic out there. And for those that are out there joining us at different spark cells, yeah, definitely visit your spark cell. They have 3D printers, and if they don't, they're probably going to get some in the near future. They'll also have 3D scanners, and and do some great stuff. I saw before you had a 3D scanner shoot bright space. I just had an ideal sitting here. Maybe you can change that into a bobblehead and then send it to him. That would be a great present for him as well. So thanks again for joining us. And anybody else have any other questions? We have one more question because we have 1 more minute left. So one more question.
Hello. For the 3D scanning, does that go as an STL file for that 3D scanner you were showing?
Yeah, that's exactly what we save it as. So it's pretty easy to send it over to Blender or any CAD program that you use. So we just scan it. The way the Artec works, it has its own proprietary program that it uses. So you upload everything on there, you cut out all the unnecessary fat, you render everything, and then when you export it, it saves as an STL file.
And I think you can actually save them as OBJ files too, in case your 3D printer needs that. But it just depends on what the requirement is.
Well, the reason I asked is we actually do a lot of machining stuff too, so we actually need to put it in like SolidWorks or something, and STL files are kind of hard to work with on there.
Gotcha.
Yeah.
So you'll have like a way of converting it over to like a solid model.
Yeah, there's several different types that we can save it as, which is pretty cool about these programs. So it doesn't just have to be an object or an STL file. I can't remember all of them off the top of my head, but there's quite a few from what I remember. So which file type are you looking for specifically?
I think it's like solid model, solid Propulsion. It's whatever it is that SolidWorks use, or something that SolidWorks can use.
Yeah, so SolidWorks can use STL files and OBJ files. I think it's got a proprietary file structure that it can use, that it prefers to use. You may be able to self-convert if you have the full SolidWorks computer software system. But yeah, it just depends. Right now, we don't use SolidWorks here in the Spark Cell. It's a little too expensive and cumbersome. We prefer using the freeware.
Yeah, but look, man, if you ever need to convert a file, if you just Google conversion websites, you can easily do that. And we've done that with JPEG as well. We've converted JPEG images into STL files, which is pretty cool. And then you can do that vice versa for any other object or file type.
We could convert it to a solid model. It's just very time consuming. I'm just wondering if they actually can convert it in the system itself.
And that's the thing. This is definitely a slow process when it comes to printing all this stuff and working on it. Even transferring everything from the Artec over to the program and rendering everything, it's not a quick process. So you sound like you're familiar with CAD for the most part, and like Blender.
Yeah, so we work with SolidWorks, a couple others too.
Yeah, but just creating those files or manipulating files, it's a challenge for working on all those, and it's just something that's just going to take time. As of right now, we haven't had to deal with any of those specific file types, and we've been fortunate enough to get away with the few file types that we do use. But yeah, sure, if there's a conversion site out there to maybe try and convert it, but.
And as computer power expands, you may be able to see that the timing reduce as well. But again, I think we're pretty much at a peak in power or peak in efficiency on computers, unless you go out and buy, your own version of a Cray computer or something like that. What's really interesting is in the next 5 to 10 years, how quantum computers are probably going to change the way we do innovation. So, if anybody's thinking that far in advance, like I do, start to look at where your spark cell is going to go and where innovation is going to go. So if you haven't, start reading about quantum computing, because I think DARPA is making the first DoD quantum internet. So they're in the process of creating that. And I just saw in an interesting article this morning that scientists are creating the world's most efficient and usable and capable quantum computer. So yes, stuff's happening very quickly.
All right, thank you. Thanks so much. And Chris, Andy, Laura, hopefully in the future we'll have more workshops like this. We do love the first person view, by the way, and you walking around the Spark cell there. That was fantastic. And thanks for joining us, and we'll chat with you guys soon.
Hey, sounds good. Again, thanks for inviting us, and it was a pleasure being able to talk to you guys.
Yep, thank you very much.
All right.
Awesome.
We'll
All
see you.
right.
Thanks for the opportunity. Take
care.
care.
Okay. All right.
All right, welcome back. I'm Steve Pileski again, and we're welcoming Jonathan Holmes and Kyle Acevedo of the Georgia Tech Research Institute. And these guys were all over the place at the beginning of the pandemic, which has made heroes of a lot of people that were just nerds before. These guys are going to talk about computer-aided design, the materials that people use in 3D printing, and then the 3D printing process. And I think you're going to be impressed with quite a bit of it. Thanks.
So I'm Jonathan Holmes. This is Kyle Acevedo. We're coworkers, and we've pulled together this presentation. Want to keep it interactive. Feel like you could interrupt us, ask some questions along the way. If there's a way to get some questions from online, I would entertain that as well. So I just want to treat this as a discussion to learn more about 3D printing. So I really appreciate the talks we had earlier today from Adrian out in Colorado. I think that was a great introductory. We're going to dive in a little bit more. We have more time to talk about this, so we're going to dive into a little more detail and hopefully learn a little bit more about it. So anything you want to say before we get kicked off, Kyle?
No, that's all good. Jonathan's going to take the first section talking about a little bit of a deeper dive into some of the more common additive manufacturing technologies. So we'll cover FDM that you guys see here, as well as some other ways of 3D printing objects, either just through a different method or on a more industrial scale. And then I'll jump in for the second half, talking about some of the actual hands-on aspects of taking a part from ideation all the way through the printing process, and then what you have to do afterwards to make it usable. So without further ado.
Yeah. All right. Thanks, Kyle. So I've got a little bit of the agenda kind of spelled out here in the slide. So as I mentioned before, it's the overview of the AM technologies. You've been hearing about a lot of different types of technologies, so we'll talk about those and when you should use AM. So we heard some examples before, but working at the Georgia Tech Research Institute, we support the Department of Defense heavily. So there is a lot of work we've been doing for the military. There are a lot of things you've been hearing about, just the broad use of additive manufacturing. But, I've been doing that for 15 years of supporting the military with additive manufacturing. So I think we can offer some unique examples of how it really does, promote the warfighter and help out our airmen and what have you. And then we're going to be talking about part 2, like Kyle mentioned. Is now we're going to go through the how do you use it, what are the steps. We've heard about 3D scanning, we've heard about Cura, we've heard about slicing. There was a great question earlier about, okay, well, what about the files? I just have an STL file, I want to be able to use it in SolidWorks. How do I work with that? We can go into that a little more in depth and hopefully introduce you to those concepts and help you understand the challenges and where you have to pay attention when working on these. So first, we're going to start out with that AM overview. So a lot of people don't realize, because they've only been hearing about additive manufacturing for the past 5-10 years, it's really become more common in people's speaking, is that it really goes back to 1981 when SLA came onto the stage. So SLA was one of the first ones that came about, stereolithography. And I will go into what these different technologies are, at least these 3 technologies, and kind of how they work. So the 3 technologies we're looking at here are SLA, stereolithography. We're talking about selective laser sintering, and we're talking about FDM, or fused deposition modeling, which is what you see with these types of machines right here. So with these machines, you're taking the filament that's extruded through, the filament that's in a hopper like this. It's extruded through, it's melted, you build up layer by layer. Whereas with SLA being the first one to come online, it's actually based more on photopolymers and curing them with an ultraviolet laser. But I think it's just nice to see that, the technologies are over 30 years old. So a lot of people just don't realize that 3D printing's been around quite a while. And unfortunately, I was able to start using it earlier in my career. So I think I've been using Stratasys FDM machines since right at 2000. So I've had 20 years of using 3D printing. So the overall process for how it works, and I appreciate the level of detail that Adrian gave us before. but I want to present it from a different perspective, how we've used it. And I think that's very valuable to see, see it presented to you in a couple of ways, because you really need to, see this and absorb it and understand how the process works to make the best use out of it. So with how it works, you start out with a computer-aided design. So very generically speaking, with the CAD side of it, you have a computer-aided design file. Some people refer to STL files or things like this that go to the printer, but I'm talking about it very generic. With Tinkercad or some of these more primitive programs, it can be just a very generic set of files that's built of blocks or triangles or circles, the primitive shapes. But ultimately, you need some sort of three-dimensional file stored in a computer file of some type that you can then turn into machine instructions that a machine like this will understand. So when you have the CAD, you just have a three-dimensional shape, and it can be presented with just straight walls, point clouds, things like this. But now you have to then turn it into something that is a slicer. So for additive manufacturing, it's almost what we call a 2.5D type of technology. We call them 3D printers, but what you're ultimately doing is you're slicing parts into multiple slices or 2D shapes and stacking them up to get a three-dimensional shape. So with that, now you look at some of these parts we have and you'll see these ridges on them. You can drag your fingernail across it and feel these ridges on it. That's an artifact of having to build it up layer by layer. But the second piece that happens in the process is you go from the CAD file to the slicing program. We're going to have a demonstration on Cura. That's a very common slicer program we're going to talk about later. But you use that to now take this, amorphous three-dimensional part, slice it into a bunch of 2D shapes. Now you're going to layer by layer replicate or produce those shapes. So the slicer is going to take that, generate the 2D shapes, now send that over to whatever your additive production machine is. So it's going to be the additive manufacturing machine that produces it. We're going to talk about the different types of machines, how they do it, go into a little more detail and talk about that. And there's another thing that's very important. A lot of people feel like you're done here. You've produced the part, it's finished, I've got an additive part, it's good to go. If you've ever used printers, that's not true at all. If you have overhangs, there's support material to remove. One thing that's very interesting is, a lot of people have seen the plastic parts. They haven't really seen the 3D printed metal parts. So this is aluminum, silicon, tin, magnesium. That's the alloy it's called, but it's essentially like a cast aluminum component. This was all 3D printed. If during a break you want to come up and take a look at these, you'll see all these weird looking features that are support features. These all have to be removed. This is what the machine had to produce when we 3D printed the part, but you've actually got to go in and remove these with more traditional machine tools, CNC, bandsaws, things like that to do it. The same goes for a lot of these metal parts. And it happens as well with the plastic parts. When you have an overhang, you can't print on just the air, you have to print on something. So a lot of these three-dimensional parts will have overhangs and will have support structures underneath them. So that's an important piece to think of, is what goes into the post-processing for that. And then over here is just that general diagram you see of how the FDM types of machine works. So I'm pretty sure everyone in here is familiar with the fused deposition modeling machines, what they're called, or material extrusion machines. What other sort of machines are you familiar with? Any other examples people have? Sure.
The resin printers.
The resin printers. Do you have a Form Labs machine here? I thought you had one, right?
I'm not sure. I'm not.
Okay, so a Form Labs, that's a, kind of a, one that's more accessible that you can get an SLA type printer. That's a resin type printer. Any others? We saw the concrete printer. That's a little more drastic of a change. We saw the concrete printer earlier in that demonstration. They're powder based, which actually that's what a lot of the metal machines are. They're using powders. But the three very common types that I gave in the introduction is the resin-based, photopolymer-based, There's the fused deposition modeling, which is the melting the plastic filament. And then there are powder-based, and they all work on different principles. And I think it's important to understand how they work, because that kind of helps you understand how to approach the technology. Before we jump into that, I just throwing out a bunch of random words here that are related to 3D printing, but I thought it's worth mentioning a few of them. And also I've introduced some new technologies in here too. So we mentioned things like slicing. Also remember that 3D printing is more or less interchangeable with additive manufacturing. People used to refer to it as rapid prototyping machines. They kind of got away from that because people realized that once you hit go and you start printing a part, it's not so rapid. So it takes a while. If you've used these printers, you want to feel like, man, I'm going to hit go and now it's going to print, you know, whatever cool Star Wars thing in 5 minutes. No, it took 6 hours. So, you know, we're getting away from calling it rapid prototyping, and it's more of 3D printing. So it's replicating a 3D part. There are some other things that are interesting here, is talking about wire arc additive manufacturing. So I am going to expand and talk about some other machines, to where when we get into larger structures that you might see flying around a few years from now, is that you've seen a machine shop just TIG or MIG welding and, you know, welding objects together, but they're actually building up entire three-dimensional parts with welds. It looks pretty bad, as you might expect, but then you come back and you machine it and you've got a really cool part that can be used. So there are some new technologies we're going to be seeing in the next few years, and you know, as airmen, it's just something you can think about, like, what can we do, what can we start doing, being forward looking about how we can maintain the aging fleet that we have in our hands. All right, so first let's talk about stereolithography, or how you use the resin-based machines. So what this is really different about this is you have the resin tank here that you see on your screen here on the left. So the resin tank, and that's similar to the machine, the photo you see there on the right with that carbon 3D machine, but you essentially have that same Z platform. We refer to this in your 3 dimensions, X, Y, and Z, is usually the layer that's traveling up and down. That would be what you call your Z axis. So the X and Y are in these directions, and Z is moving up and down. So the same for FDM, the same for resin tanks, same for powder-based. You know, you always refer to your Z axis as the stage as it travels up and down. So for SLA, you actually have this vat of liquid. I put a platform in it, and now a laser comes from the top. And, you know, think of the laser show at Stone Mountain. You're doing a laser show right on that top layer, and the laser is curing the photopolymer to where now it's hardened plastic sitting in a liquid bath. So you do that, and now I lower the stage. Once I lower the stage, now I cure some more. That's how you get that laser-based, or I mean the layer-based, you know, laser definition on the part. So a stereolithography machine, that's how it's doing it. Is you've got a resin that when a laser hits it, now it's going to cure the material. You end up with this hardened material, and you go lower and lower, but they can be very precise. You can make some very interesting parts. One thing I really like showing this example, because this seems a little bit far-fetched, but that photo in the bottom left, there's something called 2-photon polymerization. So it's that same process of the SLA, except they may just do these in a bath and, you know, just make the part, send the laser through the bath and do it that way. But we're talking about making objects that this windmill looking item you see right here is the width of a human hair. So we're talking you can make just very tiny features. These are microelectronic, you know, they're the same size as MIM type devices. So that's what we're looking at with these things. So with SLA, you can have these crazy, ridiculous sorts of intricacies in parts. And it's just something you just don't even imagine that you could make. You know, there is no other way to make something like this. It's just a really cool technology. But ultimately, that's what we're talking about, is lasers are applied, usually ultraviolet UV lasers. They're applied to a resin, and now you end up with cured material to make a part. So I think it's important to understand with these, and the same goes for the Formlabs machine you have in your lab, is what are the benefits, what are the drawbacks of some of these technologies? So with the SLA, because you do just have better, this higher precision laser that is forming the parts, is you can have much nicer surface finishes. When it comes out of the machine and maybe you drag your fingernail across it, it doesn't feel as rough. It's much smoother. The surface finish feels much better. That's a great thing. The other thing is with those, and I'm going to keep pulling from my set of parts I have right here, is I did not bring the actual mold that goes with it, but this was a prototype device we made, and this was not 3D printed. But the interesting thing is we had a very high resolution part that was printed to look like this out of stereolithography or SLA. We then cast it in a resin, like an RTV resin, made a mold, and then filled it with urethane. So now you're able to make a mold and make 10, 20 parts and have kind of this limited mold run. And now we tried out this was a soldier body unit for the Army of, something that was providing feedback on the soldiers. So this was a way to do some prototyping, and now we wanted to make 10, 15, 20 of these assemblies. Started with a very high resolution SLA. We only printed one 3D part. Now we were able to replicate it, make 10, 20 of them. So we had this kind of limited run. We could check out a few of them. So that's a cool way you can use SLA. And I'm introducing one of these terms I had on that slide before was service bureaus. So that's a term that we use for, one, there is in-house, we might have our own machines, but you might find an application to where you want to make a few more. You may want to make something bigger than it fits in your machines. So you can reach out to a company like Stratasys or, one of these local suppliers that will actually, accept a 3D part file, an STL or whatever, and print the part for you out of the material you need. This was not printed at Georgia Tech. I can't remember which company produced this, but that was actually printed at a service bureau outside of Georgia Tech. One thing with the challenges of SLA, this is one of the first 3D parts I had given to me from a supplier many years ago. I think this part's about 20 years old. And when I first received it, it was more of this, positive curvature. It's not really curved now. It's sat on my, sitting on my desk over the years. It's actually just crept and ended up flattening out. So a lot of these resins over time, they're just not as dimensionally stable. So they've improved, of course, over time. Technology has marched on a bit in the past 20 years, but there are some issues with creep in some of these resins and parts. The other thing too is if I were to take an FDM printed part and I'm going to drop this on the concrete floor, I'm not too worried about it. If there's a small feature on the edge, it might snap off or whatever. Some of the SLA resins, if we were to just drop it on the floor, it might shatter the thing. They're not as tough. They might be a bit more brittle. You might have that with some of the FDM materials you try, that it might shatter your things more readily. But they're just not as durable as some of their counterparts in 3D printing. Are there any, before I jump into the next, are there any questions about SLA? Yeah. Sorry, what was? So a lot of times the supports on the resin printers, I'm looking for an example. It's more of, this is something from a very different technology, but just imagine that I just want to print these three rods or 3 cylinders. So as I print and I build this up, even though it's sitting supported in that liquid bath, things may want to, fall over. The aspect ratio is not good. It may want to fall over. So you might put something like this in between them. So now when I print these 3, it's more stable, things aren't going to wiggle and fall over. So you might have supports like this in a SLA part. So technically speaking, they may not need them as much as some of the other technologies, but realistically, you have to have those support structures. With SLAs though, there are a lot of really good post-processing tools or the slicers and all that prep them, is that they will kind of figure it out and do it for you to where you can easily go in and remove them with a Dremel tool or a file. Because they're lighter materials, they're a little bit easier to remove those. That's a good question though. Yeah. Yeah.
To add on to that, with the FDM process, there's also dissolvable filaments as which a few of us have used in our shop across the street, and it's provided decent production. It takes a while for it to dissolve, but that's also
Yeah, that's a good point. For those of you that could not hear that, he was talking about the dissolvable supports for the next technology that we're talking about, which is fused deposition modeling. So some of the common materials you might print with, you've heard of ABS as the plastic used for them. But again, when you have overhangs or parts where, it just can't print in the air, it has to print on something. So there's a support material. What they will do is they will use polylactic acid or PLA as a different support material. Now, if I put this in a bath of sodium hydroxide, which is essentially bleach, it will dissolve that away. Like you mentioned, it does take a little while. A lot of those baths, they have to be heated and they circulate the water around. But now, it will dissolve that away and you can just pull your part out and start using it. There is one issue with that we have found that once we put things in a bath, if you've ever taken some of these FDM parts and maybe you take them out of those baths and they're wet, you blow air through it, they don't hold water very well. So a lot of the FDM parts, if I were to try to, fill this up with water, it would just leach out a little bit. Well, the caustic chemicals that are in there from removing the support kind of stay within the part. So you have to be careful if you do dip parts and put them in there to remove the support. That might cause issues later if you put it in contact with, fabrics or things like that. So these are just things to consider with the supports, is make sure that you rinse your parts a lot and get rid of that sodium hydroxide that's more or less embedded in the parts.
We did have one that was usually dissolvable in water.
Oh yeah, they're the ones with water too. I can't remember what's the water dissolvable. Is that PET? What's that? PVA. Yeah, PVA. Yeah, sorry about that. Yeah, and those work okay, but actually the PLA that's dissolved on the Stratasys machines, that works a lot better. But then you're left with that sodium hydroxide residue. Yeah, that's a good point though. All right, these are good questions. All right, so moving into fused deposition modeling, FDM, or material extrusion is another name for it, because very much like the material extrusion describes, is you have a filament that goes in. This is the filament here that would feed into the machine. As the filament goes through, it goes through a heated head. It heats it and melts that. And now as this moves around and dispenses the polymer, now that's where you get your individual 2D layers that are fused together to make a three-dimensional part. So that's where, looking at the diagram here, you have the different layers. Again, you have that Z height that's either moving up or down depending on how the machine is constructed. But then you have the liquefier head or the melting head that will melt the polymer and then build it up on top of itself and make all these layers. So it's very, very common. These are the types that are low cost enough you might see for a couple of $100 to several $100s that you could even buy for personal use. So they're pretty accessible to FDM printers. Now, one thing that's important talking about the FDM printers is I really want you to focus on that figure in the upper right, which shows a few things that are important to these parts. So with FDM, I'm not sure how well you can see this online or on the camera, but there are a couple of things. This is just printing a hemisphere, and I stop the print, middle of the print. So what you're seeing on the inside is the infill pattern. So usually the way these work when you're building your layers in the typical, the slicing programs, is you want your highest fidelity shape and feature on the outside of the part. So the external surface, you want that to be the highest fidelity, you know, the best tolerance on it. So I'm going to run a racetrack around this and define that outer layer, and then the printer will come back in and fill in the inside. Now, another very common thing is the just an angled raster like you see in this figure in the upper right of the slide. So that is more of, you know, this is kind of a honeycomb infill, but you'll also see some that just have a zigzag layer. And then just like you do when you lay bricks, you know, you go up to the next layer, I'm going to zigzag another direction to make the part a bit stronger. And how dense or sparse that is kind of sets the density of the part and also the strength and the mass of the part. So this honeycomb can be rather stiff, and you know, but it's still like a, you know, a nice viable part without having the density of it being full of plastic. Now the issue that you can run into when you start playing around with these parameters here is you might have the, you know, that contour or the perimeter that's setting the outside of the part, and now I want it to print faster, so I try to run pretty sparse on the inside. It's going to help you by running faster. It's not going to be as heavy. It's not going to consume as much plastic, but at the same time, it's not going to be as strong. You know, it's going to be sparse on the inside. There's not going to be as much material. It's not going to be as strong of a part. So when you get into these slicing programs, these parameters can become very important. Is how I want to do the infill. Is it a, you know, a honeycomb type of infill like you see with this part? Is it just that standard raster like you see with some other parts? Usually you can toggle some blocks and you know, set one or the other for the slicing program. But that's very important. And then with you know, as I mentioned before, you can see on the figure here where the axes are identified, the Z-axis being up. And the X and Y, I've seen it different on some machines. It's really not as important, but you know, the Z-axis is up and that's going to define that. So what that does mean though, is particularly with FDM, is because it's producing this by layers, and you know, I do a 2D layer, I fill it, you know, I do the contour, I do the infill pattern. That's now going to be this nice fused layer. Now I move up to the top and I start fusing it again on top of it. Maybe the adhesion isn't as good. So I look at a part that's, you know, just a cylindrical shape or something like this. Maybe the strength is better in the X and Y dimension and not as good in the Z dimension. So I'm going to have anisotropy is what you call that, to where it's not a homogeneous part. It behaves differently depending on the direction that I approach it. So that's one thing with the FDM types of parts. And here again, I just put this in the slides because I think it's nice to see where you have your key parts for it. As was mentioned in an earlier presentation, you know, looking at your manual for the various machines, I do think that's important. You know, even if it's just skimming through it for 5 minutes, you know, for this machine, that machine, there are nuances from machine to machine. So check them out and see. Did you have a question over there? Oh, okay. The one thing I want to point out is that I see in the lab a lot of filament is just sitting out. We're nice and air conditioned today. It's usually okay. The one thing about filament that's recommended as far as keeping up quality control. So if I'm just printing parts and playing around, doing test fits, things like this, that's one thing. But let's say that you know, the wing wants me to print some dust cap that we're going to start putting on, you know, installing on 40 aircraft or something like that. Now I've got to start paying a little more attention to quality control and make sure that even if it does seem like an insignificant part, if I'm not managing my filament and I don't keep it in dry boxes and I let that humidity get to it, then my prints can turn out to be garbage. You know, I can have a lot of quality control issues on my prints. So one thing we did that's a very simple thing you can do is just take your filament when it's not in use. If you plan on storing it a while, let's say I printed half the roll, I don't need this one anymore, I'm going to try a different material, is put it in a box, throw some desiccant in it, and when I say a box, maybe more like a Rubbermaid tote or something like that, throw it in a tote, and they sell some storage containers for filaments as well. But it can be as simple as throwing some of the desiccant pouches in with a Tupperware container, and that will preserve your filament. So I do think there are some tricks like that you can pay attention to, because that is one of the things for kind of novel people or new people to fused deposition modeling, is when you get humid filament and wet filament, it will start popping. You'll have a hard time controlling your prints. And that's just something to be aware of, that it'll catch you off guard. You might have a hard time tracking it down, but that's one thing that, yeah.
How can you tell when the film has been affected by humidity? Like, will it be obvious on the roll itself, or will it be like small minor?
So it will show up as minor defects in the part. So instead of extruding as a nice single filament, it looks like this undisturbed nice filament as it's printing. Every now and then it will kind of just sputter and pop. And you'll just see kind of these little pock marks all throughout the print job. And maybe they're intermittent. It might be one side one side had worse humidity than the other, but it just degrades the quality of the part. So it's this weird thing of, you might have trouble with adhesion on your plate. You might be just confused why the thing's not working. It was working 2 days ago. Why is it not working now? That's the way it shows up with humidity, or at least it can. All right. So I did just list, at least for these 3 technologies, the benefits and drawbacks here. So with FDM, you do have a ton of materials available. You've heard some of the different filament types that were discussed. You have wood filled, carbon fiber filled. You can have metallic filled, to where you almost make like metallic types of enclosures. They're not going to be as strong as metals per se, but maybe they're electrically conductive, where you care about shielding for electronic assemblies. So you might have some FDM parts like that, but there are a lot of different materials, and it's inexpensive. So for the most part, they can get pricier for the Stratasys types of machines that are made more for almost like a mini production environment. But that's an interesting thing, is just how inexpensive it can be. As I brought up earlier, anisotropic properties, where the materials are different from one direction to another, that's something you have to consider. You may have seen that with things, is that it's easy. This is another one that I've had for about 20 years that's been following me around. This was the Z-axis, the way I printed the part, and notice how it just kind of sheared and broke off the side here. So it's not as strong in that Z dimension as it is in the XY dimension, how it's produced. And then the dimensional quality, just depending on how you print this, it does matter the size of the tip, how you control the quality of the print, but that can change the tolerances on the part. And finally, I don't want to spend a ton of time on this, but I think you should be familiar with the powder-based types of technologies, because that's typically what they're using for the, for the 3D printed metals you're going to see, is that it's powder-based. So as far as how the concept works, is again, I have this Z-axis plunger, but usually I have alternating kind of powder tanks or powder reservoirs, to where I start on one side and I skim over a very thin layer of powder. Now the laser, again, similar to SLA, heats up where I want that part geometry to be. Now I, cure the powder in that sense, is I'm melting metallic powder. So I melt it. Now I create the part geometry I want. And now I start to alternate. So I lower the plate on this side. I swipe over some more metal powder from that side. So as I lower the Z-axis into the that tank or the build chamber, now my laser is curing the part, and now I have a 3D printed part. It's not just plastics. I mean, it's not just metals. So initially it was plastics, nylons, things like that have been used for selective laser sintering, is what you typically see it called with plastics, or powder bed fusion for a more generic term for that. But it's really interesting, the level of detail and the types of materials you can use there. And I thought this was just a cool figure of how it works. Is, you can imagine that bottom left image that you're looking at is you have all of these metal particles or powders that are just sitting in a powder bed. And now as the laser goes across it and drives across it, it's individually melting those powder pieces. And now that's how you cure the part. So that's kind of what it looks like. I have some sort of beam that hits powder, it melts it, and now it sticks to the layer below it. Now you end up with a three-dimensional part. And if you do have an opportunity to come up here and look at these later, you'll see that this was a part they were concerned about where there might be defects, because as the part was printing, the laser stopped, or I mean the machine stopped working, so they had to do something, fix it, and then they started it, so the machine had to kind of cool down and warm back up again. So they polished this out to see if there were any defects in between, and you can just get an idea of how solid these parts are. So there are very few voids. I mean, they're 99.9% dense, and you'll see that these are very substantial, heavy parts you're able to get out of this technology. Yeah. So for these, it can be much more expensive for the parts like this. There's one example we'll talk about later, but we printed this giant pulley that was actually installed on a crane, and that one printed for several days. It may have been 10 days where it printed. And something like that, just the machine time alone cost a lot. But to fill the powder beds that these sit in, I mean, you need this very fine powder that's good quality powder. To fill that can be $15,000 just to fill the vat with the raw powder. So you're talking a much higher cost to get into parts like that. It is with a caveat of, you can imagine that when you look at this figure right here and you think of, I am hitting something with a laser and I'm melting powders. Well, right along the edge boundary, maybe it's kind of partially fused, it's kind of not, but you're going to end up with some partially fused powder in there. The jury is out on how much you can reuse that powder, but people that have a very good quality control process, they will filter the powders and make sure that they essentially just send it through a sieve, and then they sieve out any of the large particles that might have been inadvertently welded together, and now you can reuse the powder and reuse it again. But one thing that can happen with that, you see the materials you can print with. It's really cool. Some really nice alloys you can use. They are expensive. They are slow. And the other thing too is that they can warp if they're not laid out properly. So and then you'll see that can happen with some FDM parts as well. But if the slicer doesn't process it well, or you have a weird geometry or shape to reproduce, the parts can warp and not come out as you would like them to. And now I'm just going to quickly talk about some others just so you're familiar with them. There are some material jetting types that are really inkjet printer based technologies is where they're coming from. HP has one system. There's another Israeli company that started the Object companies many years ago, to where they are inkjet printing with these photopolymers similar to the SLA, but you can just like a 3D, it's just a 3D printer based on a color inkjet printer technology. So now you see this biological looking piece right here. I think that was a kidney that they were producing. This is not an actual functional kidney, but it shows you the vascular structure inside of something. And they were able to just 3D print that as a single print part. So as far as, look, feel, models and things you can produce, it's really cool what you can make with some of these material jetting technologies. And then this is what I was talking about earlier, was the wire arc additive manufacturing, which is essentially just taking a weld bead and building an entire part out of welding. So now you take that, they look like garbage. You see that on the right side of the image. It doesn't look very good, but you can imagine that instead of taking some giant billet or block and machining, some small shape out of it, having it sit on the machine all day, instead, if I build up more or less exactly what I want and I just come back and I machine the surface to clean up the outside of it, there are definitely cases where that makes sense. So it's a cool technology and something the military has been very interested in. And I did want to give some examples of when to use AM. You know, again, we've been using it quite a while, Kyle and I at GTRI, and even some years past for me. But you'll see that there's some really nice technologies, really nice ways to use it in prototyping. So as far as easy ways to do it is tooling and assembly aids. I think that's one that's really really one of the best ways that we've found to use it. And you know, something that a lot of people don't consider too is just how you can make like big beefy parts out of 3D printing. So this is plastic, and I don't know, it weighs 5 or 6 pounds, but this is a plastic piece. But we had a wing section for a UAV that we wanted to support. We were going to try to figure out how to hold this thing and test it, but you know, we didn't have the aircraft, we only had the wing, trying to figure out what the loading is, how we can grab onto this thing. And then we decided, you know what, we're going to 3D print this, put some silicone rubber to grab onto it, lightly clamp down on it, and make a holding fixture. So it wasn't in the final delivered part, but it allowed us to get our testing done. And you know, I think this took 24 hours to print these 2 pieces, but now, you know, we went straight from CAD to 3D printed part, and you know, by Wednesday we're now testing the part. We don't have to wait on a machine shop to make holding fixtures or do anything like that. So in that case, that's where rapid prototyping really got its name. It may have been misused, but we were able to quickly you know, test some things out using 3D print technologies. Another thing is short-term repairs. You might find that, you know, you need something just fixed. A small plastic gear broke. You know that this isn't the final solution, but I'm going to 3D print a gear just to get me to working for another few hours so I can finish the job while I wait on the new part to show up. You know, there are times like that where that makes sense. The thing for AM that really gets into more advanced things, and you can see this with some jet engine examples and things like GE Aviation, things they're working on, is when you get into part consolidation. And I take something, you know, like you think about your, someone said they're interested in working on their cars earlier, that question came up, is you could take several components on the top end of your engine and just combine them into a single part. You could have never made those with castings and CNC like you are stuck with now, but I might be able to combine them a new way. So that's where AM gives you some interesting stuff you can do. Now there are times when I say use it with caution, or you more or less just shouldn't use it, is with high stress and high cyclical loading. So be careful when you get into these cases. So if it's something where it is taking on high stress, even for some of these materials that seem very stiff, a lot of studies are being done on how reliable they are over high stress and high cycles. So a ton of effort needs to go into the analysis and all that before you certify these parts. So that's something very important, is to think about that. And then high volume manufacturing. I know they brought up those examples of printing face shields and things like that. That's something that's getting up there in the volume, but there's really only one industry I can think of that's utilizing it well from a mass customization or a mass production perspective. Does anyone know one industry that's existed for several years that has relied on mass producing using 3D printing? Anyone want to take a guess at that? Dentist office is very close. And how so are you saying that with the dentist office? So with retainer types of things, so there's a particular technology. So on one side, dentist office making crowns, things like that, they actually have many CNC machines in their back office to make those. That's a different technology. But when you're talking about the retainers, Invisalign, that technology, really Invisalign, that's what it's based on. Is they take a 3D printed part and they say, here's where your teeth are now, here's where we want them to be. They print all the stages to correct you in between. They vacuum form plastic onto that, and voila, now you have your customized piece made for you for your dental correction plan. So that is actually one of the industries where they've used mass production with 3D printing. Here are some examples of where we've been using them at GTRI as well. We had our own rapid response where we were working with making face shields. Something that, again, it just doesn't seem to, it's not as obvious as we were working on earlier versions of the soldier body unit. That's what you see in the bottom left, the red and white pieces. But we wanted to put it on some soldiers at Fort Benning, have them run around, make sure they were comfortable with it and all that. They wanted it to be the right size. They wanted it to be the right weight. Wasn't even functional, but that was great. You know, we printed them over a weekend. You know, now we shipped them out, went down with them on Monday and did some field exercises, tested them out. I had the tooling where we were clamping onto the wing, but there's just simple things like that tooling piece you see in the middle there, to where I actually had a cone that I wanted holes drilled in it a certain way. And for those of you that have worked with machines as machinists or what have you, it's very hard to set up and locate and indicate off of a cone and find the place to put these holes. And we found that it actually made sense for us to just 3D print this fixture. I drop the cone on it. It has some drill bushings in it. And now with a DeWalt drill, I pop them in. So it's something that would have taken me an hour to set up on a CNC machine and indicate out. Now I was able to do in a couple of minutes with this 3D printed part. So that was really cool. And then just unique devices. We do a lot of radar and RF work at GTRI. So we've made some pretty cool antennas, and maybe there's some flying around on some of your aircraft around here. So we actually do have some 3D printed antennas that we've been flying around. This is getting back into that when to use the metal AM. So I talked about the part consolidation and GE Aviation. You know, these are some of those high-end models where we've seen metal AM used very well. So you can see in that image on the left how you're taking some very complex shapes. This is a cooling manifold, and now you're able to print that in a single part. These are just things that are very difficult to do with traditional manufacturing. And then there are items that are flying around. So GE Aviation, you know, they're working with the Federal Aviation to figure that out and get the proper approval in place. We also talk a little bit about how on the military side, working with NavAir, I know that was brought up before, using NavAir guidance and documentation to get parts flying as well. And then this was the one on the right, that is that pulley that we've talked about before of actually taking a steel pulley, 3D printing it because they were having a hard time sourcing it. And then we mounted it to a crane and lifted a 10-ton vehicle with it. So that's another thing people forget about with 3D printed parts is you can do heavy, you know, high stress stuff with them as long as you do it carefully. So when we get into the approval of parts, mention the NavAir thing and the right approval processes, is I want you to be very careful is how you use these components. Something that may seem, you know, I mentioned a dust cap or a dust cover before. There's something the Army worked on where it was just a fire extinguisher cap. So they were having issues. There was this flexible fire extinguisher cap that would snap onto inside of an MRAP vehicle, and it snapped onto it. Okay, they found a process and they got that worked out. It was a stopgap, got them through there. They were getting some vehicles up and running, and now they moved on. But then you think about that, and what if this simple dust cap were to prevent the fire extinguisher from going off? You felt like it was a quick fix, it works great, but now your printer parts come out and they come in undersized for some reason. Or, you know, they're not quite the size you expect them to be. You give them to some people to install, they're tight going on, they'll just whack it with a hammer, they'll put it on. But in the end, it's not going to allow the fire extinguisher to do its job, maybe. So, I mean, they went through the right sort of procedures to get this in place, but you have to think about that. Is it something simple, or could it maybe impact human life and safety if I were to use this? So that's something really important is you know, think about that and consider these parts where someone may hand it to you thinking it's something pretty benign. This is just a door stop. This is a button that I press on a flight control. What if that button falls off? Now, did they lose access to that flight control surface? I don't know. So think about that before you start getting too much in your hobby mode and fixing things. You know, just have that in the back of your mind when you start printing these parts. And then when it gets into printing real flight components, well, that's a bit different as well. You know, these are real structural stressed members. There was a huge study between Johns Hopkins University, Penn State, NavAir, where they were working on replacement parts for the V-22. They spent millions of dollars. You can see that for, I think, 3 or 4 linkages, that bottom right image shows all the test pieces that go with it. So that is the plate that a powder bed fusion machine does, the same one that made this cover right here. And that's how many test parts they have to print with it, just to pull on them, stretch them, break them, and make sure that the parts they care about are of the right quality. So in the end, clearly it would make more sense to just make new ones out of billet and machine them out. But they are doing the research now to try to figure out what does it take to make sure that we can, safely put these on vehicles. And then, there are things that you can go through about the source approval and TDP guidelines. So if you start dabbling in that and you start thinking about, printing approved parts and all that, there's a whole new set of challenges that go along with that. So just make sure that you know where to look and you go for that and look for it. And I did have a, this is more for the textbook style, what are the printers, how do they work and all that. If you get interested in that level of detail, there are lots of text and books out there to study in that. And they go through the math that goes into it. And it's kind of interesting for me. I like that sort of thing. So that's interesting to see how these different technologies work. And then there's also an international set of standards for what the terminology is with it. So if you don't understand some of the terminology, you're wondering what these words mean and all that, there are places and online resources to go looking for that. So I do encourage you, if it's something that's interesting to you, to go out and look for it. There are a ton of great resources out there. So we're set up for a short break. Are there any other questions before we take a quick break?
All right. Thanks, Jonathan. We're going to take a quick break, and then we'll let you guys get on to part 2.
All right. Thank you.
how you want to monitor the actual printing process itself, and maybe some things to troubleshoot if you're having trouble. And then we'll get deeper into that post-processing workflow that Jonathan mentioned earlier, and some of the things you need to worry about once the part is off the printer. So how do we think about part selection? What do I actually want to print? And this is actually big business across the Department of Defense. So GTRI, we actually have sponsored projects. We're working for multiple branches, answering exactly this question. And the reason it's such a big deal is, as you've heard alluded to earlier today, you know, when you have a vehicle platform or an aircraft platform, they have huge sustainment needs, huge maintenance needs, and it all flows down from DLA, the Defense Logistics Agency, and then, you know, it's just an enormous beast that needs to keep moving and keep fed to make sure that your aircraft are ready to fly when they need to be. But sometimes that process breaks down, and so especially when you have things like legacy platforms, every time the A-10, you know, saves itself from the axe, and now it has to be sustained for another 5 years. You have an aging fleet of C-130s. You have land-based vehicles like the amphibious assault vehicle in the Marine Corps. These things get older, their supplier base drops out, and now you start having logistics and sustainment issues. And so that's where additive manufacturing can be a huge win, where the government in general or the DoD may have trouble getting anyone to make the part the way it was made originally, but you might be able to print it. So how do you figure out if the answer is yes or no, right? And so the way we do that is we really split it up into two primary questions. One is, can I print it? And what that means is, can I accomplish the technical objective, right? So with the 3D printing processes that I have available to me, can I get an acceptable version of the part that I'm trying to recreate? And so that comes down to a few different factors. So, you know, if it's a part that's going to go on a vehicle, what was the original loading? What was the original use case? Like, was this part under a lot of stress? Is it an interior doodad that occasionally gets touched, or maybe even doesn't get touched at all? Well, those place it into different categories. What's the expected lifespan? So do the materials that I can run on my printer, are they going to perform, you know, over a 20-year lifespan that this part was originally expected to perform over? And then what are my printer capabilities? So there's some very obvious questions about geometry, like, is it going to fit in the build volume? Is the printer that I have on hand going to give me the resolution that I need? And that might affect, you know, both my choice of technology, but also whether I decide to make an attempt at all. And so the final thing is data availability. So if I'm trying to recreate something, do I have an appropriate data source to recreate that part? And so when we're talking about, you know, on an industrial scale, the logistics chain, that's a huge deal, because if I'm going to 3D print an engine linkage for the V-22, I need to know exactly how that part was designed, how, you know, how they expected it to work, what the original designer's assumptions were, all so that I can properly qualify my copy that I've printed. If it's a form fit prototype, you know, I don't necessarily care if I have the original drawing set or the original engineering assumptions. I can go ahead and try it out. It's low risk, low cost, right? And that's really the beauty of 3D printing, is that it allows you to iterate so quickly with very little penalty, as long as you consider the downstream ramifications. So then we come to this second question, which is, should I 3D print it? And so now we've moved beyond the technical capability of will I get a usable part, into some additional considerations of things like that risk level. You know, so does this represent a critical function for whatever I'm going to put it on? We start to consider things like relative cost. Like, does it even make sense for me to print this versus making it how it was originally made? Like, for certain parts, this is a great example, right? Jonathan talked about how expensive metal powder is, how expensive those machines are. It's definitely not a low cost process. Now, it has some incredible capabilities, but if I want a relatively plain bracket like this, printing it on my fancy metal printer is probably not the best way to do that. This would be quicker and easier to just send to a machine shop and get it machined in a traditional manner. But in this case, there were specific objectives and they wanted to try something, and so that's okay. But it's an important consideration. So this flow chart really talks about the whole process of production. So once I've decided what to print, I have to, first I start off by getting the geometry that I need. And so we've mentioned a few avenues for that, whether it's reverse engineering, using pre-existing models. Then I need to get it into an intermediate format. So that's where that STL file comes in. And we'll talk a little bit more about that in a moment. And then from that neutral file format, my STL, I put it into a format that the actual printer can understand, and that machine carries out that set of instructions. So typically in the manufacturing world, we call those instructions G code. And so what your slicer is doing, and again, we'll demonstrate, is your slicer is taking the STL, it splits it up into those layers, and then it translates each layer into a series of numerical instructions that's just telling the printer exactly what to do. So this printer is a pretty dumb machine at the heart of it, right? It cannot infer anything about what you're trying to print. It needs to be told, go to this point, spool out the material at this rate of speed, go to the next point, raise up by a fraction of a millimeter. And so that's what's happening with that machine code instruction. So, as the technology evolves, you have some increased capability in terms of being able to monitor your process. And so a consumer grade printer like this, I'm sure you've all seen, if you've used one of these before, you've seen examples of what you call spaghetti, right? Where a print goes wrong in the middle or it starts to lift off the bed. You come back to it an hour later and it's just a mess. But as things mature, machines are getting better at being able to monitor themselves, look out for errors. In fact, in some industrial settings, they're even using things like machine vision and other sensing to actually be able to tell when a process deviates from what you expect, and it can warn the operator. And just as the technology has trickled down from being only accessible to an industrial base. I mean, you think about these things 10 years ago, to get one of these, you were talking about a $100,000 investment, right? And now you can get a small one for $200. And so that evolution has been amazing. And so those continued innovations will keep trickling down to a level that's more accessible to labs like this one and individuals. And then finally, so once you have your successful print, you need to worry about post-processing, which covers part removal, part finishing, inspection, and we'll go over those in detail as well. So reverse engineering, I think, we've covered the scanning aspect pretty well. Primarily the previous presentations today focused on laser scanning or image-based scanning, which is a great tool. There are other options. I don't know if any of you are familiar with, say, a Faro arm. Have you guys ever used anything like that? Okay, so Faro is in general an instrumentation company. They actually make laser scanners as well, but they also make general metrology tools, which is the art of measuring things. And so a Faro arm, as we refer to it colloquially, is this, it looks like a robot arm, like what you might see in an automotive factory, right? It's articulated at 3 different points, but you move the head around manually, and at each joint of the arm, it has a very precise ability to measure angle and position. And so you place it on your object, and it has a little probe, and I can put the probe on the outside of the object, take a measurement at each point, and build my point cloud that way. So there's just a variety of different ways that you can get that end result of taking something that already exists and getting it into a computer generated format for further manipulation. And there are additional things to consider when you're trying to do this. So first of all, how good was your measuring system? And so this is a big concern, particularly with the scanning systems, because they can be thrown off. I mean, you have things like reflectivity, surface variation that can either trick or just affect the accuracy of your sensor. And that means that you have to go back in and double check that the geometry that you got is what you were trying to get. Another thing that is worth talking about is being able to manipulate that data after the fact. And so there was that question earlier, how do I get something that was scanned into a part that I can manipulate in a traditional CAD program? And it's actually a surprisingly difficult problem, because if I'm scanning something, I'm basically building what you call a point cloud. So I'm bouncing either my laser or in the case of a camera-based system, just light off of an object, and then the computer is attempting to measure how that laser or light is reflecting. And so it does that at hundreds, thousands of individual points and builds up a surface, right? But the scanning system itself has no way to determine whether the idealized version of something. So let's say I scan that wall in the back of the room. There's going to be some natural variation in the wall, but on the back end, on the computer end, I don't know for sure whether that was supposed to be flat. So in CAD, if you were modeling the wall, it'd be a single flat surface. But with a point cloud, I then have to go make assumptions about where each feature is, what the boundaries are. And so it's a difficult problem to recreate, and that's why it ends up being time consuming, because if you truly want a model that you can manipulate further, a lot of times you have to take your scan geometry and rebuild it as a feature-based geometry in order to make major modifications. So talking about that CAD process, we've had a few CAD systems get mentioned in the previous presentations. There are a lot of them out there. What are you all familiar with? What have you used in the past? Or what do you use at the lab? Autodesk, Fusion 360. Okay. Yeah, and that's honestly a great option. I'd say Fusion 360 is probably one of the more robust packages out there that is relatively easy to get for free or low cost. There are plenty of other options. Some of them are free, some of them cost a little money, some of them cost a ton of money. G2I tends to be a SolidWorks shop. It's a great program. It's gotten progressively more expensive over the years. The important thing to note about CAD is there's actually two different primary workflows, if you will. And so there's what we call parametric modeling, and there's direct modeling. And so I think you heard Adrienne talk about packages like Rhino and Blender. So those are examples of programs that use what we call direct modeling. And what that means is that you're manipulating the geometry directly. So if I were to create this surface in Blender, I'm going to push and pull and change surfaces, visually in the program. And the corollary to that, when I say parametric modeling, what parametric really means is that it's driven by equations, features, and constraints. But what it means in the context of the CAD world, for the most part, is that I have what's called a feature history. And so if I were to make this part, or actually let's look at something simpler just to make it easier to demonstrate. If I were to make this bracket in a parametric modeling program, I would start by drawing a sketch in 2 dimensions of maybe this surface. So it's just a rectangle. And then I would extrude that surface to create this bottom part. And so that's now one feature. And then I would create another feature to sketch and extrude this leg. And then I could either do it again on this side, or I could mirror it, right? And then I place my holes, so on and so forth. And so you end up with a tree that records every action that you've taken to make that part. And so that is pretty much exclusively what we use in the engineering world, but both methods are equally valid. I would encourage you to play with them. There are free solutions on both sides of the coin, and you can see what you like better. The thing to note about some of the free options is that their capability can vary quite a bit. So something like Tinkercad, the first one on this list, is extremely basic. It's going to allow you to do stuff like this. It's probably not going to allow you to go much further. And so as you move up the chain, Fusion 360 is actually a very powerful program. But generally, as you move up the chain, or when you start paying money, you get some more advanced features like complex curves, surface manipulation, and things like simulation. So particularly if you are building a part that's actually going to be deployed somewhere and you want to know how it performs under load, that's a whole nother ballgame where you can actually plug that into a numerical simulation and try to figure that out before you make and test it. So what if I don't want to reverse engineer something, or I don't want to model it myself? Well, again, Adrian talked about existing databases. There are a ton. I'm sure any of you who have been exposed to 3D printing, you've probably heard of Thingiverse. It's not the only shop out there. It's probably the closest to being like a de facto repository, but in my opinion, it's actually been a little bit stagnant for a while in terms of what they're doing to push features forward and boundaries. And so that's something worth exploring if you're just looking for models. There are just an amazing amount of resources out there. So this is a list, you know, I won't necessarily recommend any one over another, but it's definitely good to get a feel for what's out there and explore multiple sources if you're looking for something. I mean, it's actually pretty incredible what you can find between all of these different sites. I've seen like down to the part level models of entire airplanes or motorcycles, what have you. And then finally, what I'll say about part selection and how to figure out what you want to make is think beyond just 3D printing an object for end use. And so, you know, one of the amazing things about additive manufacturing is that it can touch and improve literally almost any discipline that you can think of. And so something that we use quite a bit at GTRI is using additive for tooling. And Jonathan mentioned that, but you know, you can do, what is the expensive part about injection molding or molding a part? It's the mold creation, right? Because normally you have to have somebody machine you a mold out of a very expensive piece of tool steel. Well, guess what? If you just want to play around with part molding, you can 3D print a mold. In the upper right, there's an example of that. And now obviously, you know, if you're working with polymers, you're limited to casting materials that are softer than whatever your mold is made out of, but it's still incredibly powerful. And then on the lower right, you can actually see that's a polymer press tool that's being used to form aluminum sheet. And so you can get pretty fancy and actually recreate some processes that you typically find in a fully featured machine shop, but people are doing this in labs like this one or on their own. In fact, I know we had a couple of car people in attendance. I'm a little bit of a car guy myself. One of the coolest things that I've seen is this guy on YouTube was doing a resto mod of an old, it was a classic pickup, and he needed body work, and rather than try and slather Bondo all over it and fix, you know, the rusty panels that he had, he was actually printing dies and pressing new aluminum panels so that he could put on his truck. And it came out really, really nice. So there's just a ton of options, and it's important to think about, even if you think, can I print something that I want? And the answer is no. Then you can move on to, can I use my 3D printing to either learn something about the process or make another production process easier? So now we're moving into the next phase of, okay, I've decided what to print. What do I need to do next? And this gets us into design for additive manufacturing. And again, we can break it down into a couple of primary questions. One is, how is my part going to be different from the one I'm trying to replace? And so that's things like, are my material properties different? Maybe I just don't have the exact same plastic that something was made out of, and I need to account for that. But then there's another primary question of, how can I take advantage of unique additive manufacturing capabilities? And so that gets into some of the really cool boundary pushing elements, which are things like part consolidation. So I don't think we were live, but we were talking about this bracket. this is a fairly simple bracket. It's not that exciting from a geometry perspective, but what's cool about this is that this started out as a small weldment. This was actually a 3-piece weldment. You had a flat plate on one side, flat plate on the other side, and then this curved piece in the middle to join them all together. And so this, you wouldn't think that this was a great 3D printing candidate, but when you added up all of the production and welding labor, it's actually not a bad deal to throw this on a metal printer. And so that's what they did, and it came out well. So you can look at part consolidation. You can also look at the unique ability that 3D printing has to create very complex and multi-scale geometry. So it doesn't really matter how big my part is. I can create features that are all the way down to my machine resolution, and I can do that as many times as I want. And so you get into some really amazing things as far as lattice structures. You can take weight out of a part without really reducing strength, and you can do that in ways that are not always possible with more traditional machining or molding methods. So to look at an example, and this is one that Jonathan mentioned. So this, what you see pictures of here is a crane pulley that we worked on for the Marine Corps. And you can't really tell from the pictures. This is about 14 inches in diameter. So this thing, I mean, you got to use both hands to pick it up off the table. And what you're seeing in the center image is just an example of where we had to make modifications in terms of design for additive manufacturing. So we had the original part geometry, and you can see that cross section here in the center of the slide. And that's the pulley cross section middle. In that center concave area is where the big wire rope of the crane sits. But for the original part, you had some tight tolerances, and you also didn't want too much surface roughness because you don't want that wire rope to wear down, right? And so what we had to do to print it was we actually added material where that red line is, and then machined it down later. And so we weren't directly recreating the part, we were recreating a modified version that then went to post-processing to get us the end result that we wanted. And so when it comes to FDM, there's some additional things that you have to think about. Surface finish is one of them that kind of applies across the board. And as Jonathan mentioned, it varies depending on the technology you're using. You also need to think about things like overhangs and horizontal holes, because since you're building this up layer by layer, as you start to get overhangs, there's nothing underneath that layer that it's trying to print to support it. And so this is a great example. So this is a test piece that I think was originally designed by Autodesk. And basically this is a grading rubric to both assess and then dial in FDM printers. And on this little piece, and you guys can take a look at this when we're done, there's a number of different features that help you dial in individual settings for the printer. And one of those is overhangs. And so this sort of archway right here slowly increases the overhang angle. And I don't know if you can see it clearly, but as you look underneath, the steeper that angle gets, the more your surface finish goes to crap. And so that's something you have to consider in the design, and you have to make the decision, can I change the orientation, or do I need to add support? Or maybe in some cases, I actually need to change the design itself entirely so that it does the same thing, but it doesn't look the same. And then you also have to worry about things like tolerances. Can I achieve those tolerances on the printer that I'm using? And then Jonathan already talked about infill percentage and how that can have a big result on your resulting part strength. And so here's a little bit more on that cool part of DFAM. This isn't just an example of, this is an aircraft bracket actually. And you can see the different stages of optimization. So they started with the bracket you see in the upper right, and that's built using a traditional process. And so you can see where they've machined out pockets or drilled holes, and then they went through a series of evolutionary stages to get the end result that's below it. And so you can see that all the material that they've removed while still maintaining the ability for that piece to carry a load. And then on the bottom of the slide, that's just another example. That involves not only topology optimization, but also part consolidation. So that was an assembly made up of 8 components, 8 different brackets that were all bolted together. And now they've made it into a single part. So we've chosen our part. We have made any design tweaks that we need to for additive manufacturing. Let's talk about pre-processing. And so normally when we talk about pre-processing, we need to get our geometry out of our, well, if you're going direct from a scan, we need to get it out of our scanning program. Or if you're manipulating something in CAD, we need to get it out of our CAD program and into a neutral format so that that machine code can be generated. Now, the most ubiquitous neutral format in the 3D printing world is the STL file. And what you're talking about with an STL is you take your geometry. And so in this case, if I have 2 concentric circles, you know, maybe it's a tube, an STL is going to break those circles up into a series of points, and then it's going to connect all those points with lines to make triangular facets. And this works pretty well, but there's a few limitations to keep in mind. So first of all, in between those points, I only ever have a flat surface. So it doesn't matter what my original shape is, it's always going to be represented with triangles. And so you have to be careful that the resolution of your STL is appropriate for the size of the features that you're trying to recreate. And so this is actually one of the most common things we see with beginning 3D beginners trying to do 3D printing, is that they'll export a really nice looking model to an STL, but they'll export it too coarse, and then they'll wonder why things look so rough when they go to put on the printer. So that's always worth checking. Another thing I'll note is that the STL file format, oh yeah. What's up? Yeah, so typically, I mean, if you notice that you're getting visible faceting on a part, the first thing to check is to go back and whatever you originally made that STL file from, it should have settings that control the facet count. You know, it depends. Some of them will let you control the number of facets as an absolute number. Others will just have sort of like an accuracy slider. And so you just want to try recreating that in a finer format, and that should give you better results. Sure. So the other thing I'll note about STL, it's ubiquitous. You will run into it. You will probably have to use it. It's also really, really old. So it was originally designed, the file format was designed for 3D systems in 1987. So just like anything from 1987, the world has progressed a little bit. And so there are probably arguably better ways to represent geometry like this. One of them that I'll point out, there are a few different standards. The one that I think actually has a chance to supplant or surpass STL is called the 3D manufacturing format. And so as a file extension, you'll see it as 3MF. It's essentially an evolution of the same idea. So you still break your geometry up into points and you're connecting the dots, but it has some features that are very handy, particularly when you want to 3D print something. So first of all, you can store color and texture within that file format. So, you know, one problem with an STL is that you lose any information other than the geometry. So if I decide, well, I want to keep the STL because it's neutral, I can open it in a bunch of different programs, I essentially just have this featureless blob of whatever is in there. 3MF solves that to some degree because you don't lose color, you don't lose texture. It supports additive manufacturing specific metadata, so you can attach things like infill information to the file. That's still kind of an evolving thing, but it's out there. And then finally, 3MF can represent curves in between points rather than just straight lines. And so it actually, for a similar file size, you can get a lot closer to your original geometry without cranking up that resolution, which can be really nice. So Cura, actually a lot of the common slicer programs, and in particular Cura, which is one that we're going to demo today, they support 3MF natively. And so you can, if you use a program that'll export to it, you know that you can print it. And so I actually really like working with it, but you know, either way works. All right, so next we're gonna take our neutral file format, STL 3MF, and we're gonna slice it. Again, this is to generate our machine code. And what we're doing here is we're defining, so with that STL, the slicer is gonna split it up into layers, and it's gonna control all of those parameters like temperature, feed rate, how thick is my wall, how thick is my infill. And you can control all of these things. It's not necessarily always a good idea to control them all, but you do have very fine-grained control over every parameter that gets spit out. So here on the screen, there's a few examples of common programs that'll do this type of work. Mesh Mixer is primarily a tool for manipulating that intermediate geometry, so you can actually directly manipulate STLs. And a reason you might need to do this is in the video in Adrian's presentation where he had an issue with the scanner not quite picking up that feature. Sometimes you'll get weird things with either a scan or a generated STL. There'll be a problem with the geometry. A tool like Mesh Mixer allows you to go in and repair that. Cura and Slicer are both exactly what they sound like. They're used for actually making those slices in your machine code. Finally, we'll talk about support. So, you know, if you have overhangs or holes, as we mentioned, you need to decide whether it's worth adding extra material to prop those up during the print. And that's really, it's just a trade-off. I mean, you know, it's never a bad idea to have support, but you need to realize that it's going to increase your material cost, it's going to increase your printing time, and depending on whether you have a multi-material head, so if you do, you can use dissolvable support, which allows you to remove that pretty cleanly. If you don't, you can still use support, but you have to mechanically remove it. And so what, you know, they're actually pretty good these days, the slicing programs, about adding support that kind of just barely attaches to your part. So it'll either break away or it's easy to cut off. But, you know, it usually leaves some sort of evidence that it was there. And then you can control the support type as well. And normally you don't have to do that, but things like, so looking at those heart shapes, something like a concentric support is really good if you want to print, for example, a sphere, because it's going to support the sphere very evenly as opposed to, say, a lattice structure. All right, so real quick, we're going to show you guys what that looks like using Cura. Did you want to do this, John, or you want me to? Okay, so what I have here is exactly this red piece, this 3D printer test that we showed you guys. And what has already been done is I just went over here to this open file dialog and imported my neutral file format, so STL or 3MF in this case. And what it'll do is it'll drop it right on my build platform. Now, if you're using Cura for the first time, if you're using it in a lab like this, it's probably set up already for the print resources that you guys have, but you need to make sure that your correct printer is selected. And there's a ton of different presets. These are the ones that have already been defined for this Cura installation, but you can manage your printers, and they have default settings for most of the machines that are sold today, which is really, really nice. And then you can go in, you can also define your material. So I have, right now, I'm saying I'm going to print PLA. If I want to switch to any of these other choices, it'll adjust the machine accordingly. And then finally, here's where you get into the meat. So by default, Cura is going to give you a number of different default print profiles. And so you can see right here, and this might be a little small, I apologize if it is, but I have a fine print profile selected, which means that I'm using a layer height of 0.1 millimeters. And what it's going to do is it's going to go through all these different categories: quality, shell type, infill type, material speed, and it's going to adjust them to get, you know, what it is defining as a fine print. I can put it at normal, which gives me a layer height that is 1.5 times that, so 0.15 millimeters, so on and so forth. Now, if I want to tweak anything, and honestly, I mean, in my experience, Cura does a good job with the default settings. So my first angle of attack is always to try something out with the default profiles and see how it does. But you can go in and change any of these things that we've talked about today by drilling down into these categories. And so shell, I can define my wall thickness. I can define my infill percentage, or my infill density as a function of percentage rather. This is actually probably one of the more common changes you'll make if you want to make a part stronger or lighter. You'll move that up or down. And then you can get into some really advanced stuff like, what is my fan speed? And that can come into play if you're having issues with, for example, warping, because you want to control the cooling rate of the material after it's printed. So when I'm happy with that, I'm going to go over here. I'll click the slice button, and usually it's pretty quick. And so now I have a preview. It's telling me it's going to take 34 grams of material, and it's estimating a print time of 4 hours and 3 minutes. That's not always spot on, but it's usually a good order of magnitude estimate. And then if I'm curious, or if this is a particularly complex print, I can click the preview button, and it's going to show me all of the different layers, and it actually color codes them. So I can use this slide on the left to drill down. And so you can see exactly what it's doing in the middle of the part. So, you know, inside this column here, it's hollow, and it's replacing that geometry with the infill pattern that I've defined. So if I'm happy with that all the way through, I can save it to a file, which is usually, in our case, a removable device like a memory card. And that memory card, so that will take the generated machine code and allow me to stick it in my printer. You can also network printers in Cura, and it actually has a monitoring function for that. So if your printer is networked, it'll allow you to see your build status. It just depends on whether that's, you know, something you guys want to take the time to do or not. All right, so I think we'll probably have to start moving through this quickly here because we're running short on time, but this is actually a good topic to spend some of our final minutes on. So FDM materials, there are a few common ones that you're going to see more often than not. PLA is a big one. It's cheap. It's easy to work with. So most printers out of the box can print PLA without too much trouble, or at least with minor tweaking. The disadvantage is that it's not great as an engineering material. So it degrades under UV. It is pretty brittle. So you'll notice, like, if you print something out of PLA, if I were to take one of these little posts and start tweaking it, I could snap one of those off, no problem. It's not going to move very much before it fractures in a brittle manner. But if I'm just trying to do like a form fit type prototype, PLA is a great option. You'll see a lot of ABS, which is sort of stepping up the chain in terms of its material properties. So it's durable, it has great chemical resistance. A lot of things that are made commercially with plastic are made out of ABS, but it's much more difficult to print with. And so when you move into some of these stronger materials, you start requiring higher build temperatures, and you also start running into problems because of those high temperatures. You often will need a heated build volume. So, you know, obviously the print head's hot, the build plate is hot to a lesser degree. When you start printing ABS in particular, nylon is also another big one. you often will need to heat the air volume around the printer. So a printer like this is not going to be a great option for printing those materials unless you have an enclosure around it. And what happens if you don't properly heat that air volume, the most common side effect is warping. So it'll start to curl off the build plate, and that's because you have to get that material screaming hot to melt it. But then as it cools down, if it cools down too fast, that starts to pull on the other layers of the part, and those thermal stresses build up until it curls up like potato chip. The last two materials we'll mention, this is an example of Ultem, which is something that Stratasys pushes a lot. It's a really good engineering material. It's also pretty expensive. And you can also do some interesting things like make watertight containers with it, which is sometimes difficult with FDM. And then finally, you can print flexible materials. So this is an example of a TPU part. It's probably too small for me to show you guys, but if you want to come feel these, I can bend this with my hand. This is actually, so I said I'm a bit of a car guy. I have an old Porsche 944 at home. And this is a little gasket for like an inspection port that I made. And it worked great. Okay. So still on the topic of materials, Jonathan mentioned anisotropy. So who knows, who can tell me what isotropic means? Not quite.
It's strength in each axis. So like if I bend it and then rotate it 90 degrees and then bend it and rotate it 90 degrees and it's the same strength.
That's right. Yeah. So something that's isotropic. So isotropy in general means something that is the same in no matter what direction I'm measuring it. And so anisotropy is a big issue, particularly with FDM. And the reason that it is because of that layer-based deposition. So on the slide here, you can see cross section. So what they did was they printed a bunch of test coupons, and then they took cross sections, and all those black areas on that image on the right are voids, and they're voids primarily in between layers. And so you can imagine with that much empty space in between the layers of the material, it's going to lead to some very different strength properties. And so on the left is an example of a tensile test. They went and pulled these things apart, and you get very different results depending on which axis the part was printed in. And that's definitely something to keep in mind whenever you're engineering something. It ties into that DFAM process because your strength can be actually multiple, along the X and Y axes rather than the Z. So we'll fly through these. The printing process, again, you can tweak all these things. The biggest takeaway here is if you're having issues, slow it down. So you'd be amazed at how many common printing problems you can solve by slowing your feed rate down. And then you can iterate on some of these other things like support, temperature, adhesion. Post-processing, there's a lot of different elements to this, but getting it off the build plate, it's usually pretty simple with FDM. You can also get flexible build platforms that help with that. You can use a sacrificial layer like painter's tape is a common one. There are options. Support removal, we've talked about. I won't spend a lot of time on that. Finishing, this is a big one. So you can sand parts to get a better surface finish. You can blast them. With ABS, you have a really interesting option, which is called vapor smoothing. So that you put this, you put a part like this in an acetone vapor bath, and it actually like lightly melts the surface of the part, and it gets it to a mirror smooth finish. This actually had an additional graphic applied to it at the end, but you can see how smooth the part itself is as opposed to the other side where you can see the layers. Hardware is a big one. You can print 3D print, or you can print threads in 3D printed parts. I don't necessarily recommend it, especially if they're small. So as a general rule, we try not to print anything threaded under about M8 or 5/16. And if you want to go smaller than that, you should use inserts. And so you can get press fit inserts, or ones that work really well are heat set, where they have special tools, but you can just use a soldering iron. You print a hole that's slightly undersized, then you heat up the insert with your iron, and you just slowly press it right in there. And that's what you can attach your hardware to. And then finally, talking about inspection. So, I mean, the same idea applies as with traditional manufacturing. You can go as deep as you want with quality assurance, but you have some additional considerations. So you want to take, when you get a finished part in your hand, you want to take a look at, how is my layer adhesion? Was it, is there visible porosity? And I can show you some examples up here of different iterations where, maybe the filament didn't fuse as well as it should have. And it's just something to watch out for, again, especially if you are doing something that will apply stress to the part. And that is all I've got for you guys. So does anyone have any questions before we wrap up here?
We're talking about the point cloud from our scan, and then the STL sounds like that's at least based on points on the surface as well. Is that not translatable through the software? Are those different points, or how does that work?
So, and this is going to come down to individual variations between vendors, because a lot of vendors for those scanners have their own proprietary software. But I mean, the simplest way to take a 3D scan, which generates a point cloud, and get it into usable geometry is you literally just connect all those dots with facets, and that becomes your STL. Now, I think there are solutions out there that try to be a little bit smarter. And, again, we use the wall example. Like, they might say, oh, all these points are forming what really looks to me like a flat surface, so I'm going to make that a single surface. But in general, that's exactly what you're doing when you create that STL. Sure.
Any other questions?
All right.
All right, great. Thank you so much, Kyle and Jonathan. I'd like to present you with a 3D printed coin. Have you guys 3D printed coins before at Georgia Tech?
I don't know. This
Hopefully
is pretty cool.
This is here you go.
Cool. Thank you.
For you and
Very
for you.
awesome. Thank you.
Thanks for joining us. Yeah, it was really great. And thanks for taking us really in depth and bringing all these 3D examples here, 3D printed examples. As you can see, you can get very, very detailed and very like really fine finishes as well, and different techniques and whatnot with 3D printing. And thanks for sharing your stories as well. There's a lot of folks out there doing great stuff, and you guys drove down from Atlanta to join us and join you guys virtually and share these special stories with us. So thanks again. I really appreciate it.
Well, thank you for having us.
All right. So today, that's probably what we have for a store. And we went from Mars and NASA, right? Innovation kind of culture event to kick it all off. And then we went into 3D printing overview, went into scanning, and then materials and CAD design, and then actually 3D printing. It was a great day today. I'd like to thank some special folks that made this happen. There's a lot of airmen that volunteer their time here at the Spark Innovation Hub here at Robins Air Force Base. So I just want to say a couple of names. So hats off to A1C Morales and Senior Airman Philipore. Those are the folks that are behind the scenes, bringing this live, this whole event and getting this going. Senior Airman Marsh for kind of coordinating this. A1C Draskovich for helping out with the guest list. Sergeant Orr, Sergeant Head, Lieutenant Wong, Major Pileski, thank you so much. Lieutenant Lancaster for actually getting food. We had some food while this was all going on, and she made sure that our guests were fed. And of course, Colonel Carnes and our special guests.
Yeah, I just want to thank again Ms. Cloud with Sustainable Sun Systems, who also started Spark Making here. Gary Hart and Jay Flesher from Middle Georgia State University and Firestarter Fab Lab, and Sergeant Andy Renteria from Joint Base Andrews with their Spark X cell, and all the guys that work there, to include all of his coworkers, and then obviously Georgia Tech Research Institute. And finally, I just want to say thank you again to NASA and the Jet Propulsion Lab for and Mr. Rob Manning. So
yeah, it was a great day today. Fun and exciting. And we're actually going to do this all over again tomorrow. For those that missed out on today's event.